So, welcome everybody. Welcome to this workshop on Design for Change, Software Engineering to the Rescue. I'm glad that so many people found the way to this room today. Happy to have you all here, and also thank you very much for having us here at this conference virtually in the UK. I'm here today with my colleagues Sören Peters and Sven Markus, and my name is Jan Linksweiler. You can identify these guys, but they have the same background as I have. So we are all from Braunschweig, Germany, from the Technische Universität in Braunschweig, and we are here today to share some of our experiences in software development and software engineering. So our background is in computational fluid dynamics. Computational fluid dynamics is very compute intensive, so we deal a lot with high performance computing. So usually we do this workshop in C++, but we decided to do it today in Python. So we guess that most people are enjoying this language nowadays. So we will see how this works out. In general, we think that it's a good idea because it's a workshop to get into interaction with each other. So for the moment, it would be nice if you mute your microphone so that we don't have these background noises or stuff. But once you have questions, feel free to interrupt me, to interrupt us anytime. So just unmute yourself and say you have a question, and also it might be nice to have a picture of you to turn on your camera and then just discuss a little bit. So I guess it would be good that we have a couple of breaks, roughly every hour, every 1.5 hours or so, and we have a larger break during lunchtime at your time. So I guess your time, 12 o'clock, something around this, will have a 30 to 45 minutes break that you can have lunch. But also, again, if you have the feeling that it's enough for the moment, then just ask for a short break so that we can interrupt any time. What are we going to talk about today? So first, the first part will be a more theoretical one. We will talk a little bit about the requirements for software to be sustainable, to be maintainable. We will identify all the characteristics that might be good for high quality software. And then we will go on and take a look at best practices, at patterns and practices, so solutions that work well and have been working well for other people, so that we can rely on the experiences of other people in order to build good quality software. And then in the third part, we want to have a hands-on session. So that's the part where at least the two guys next to me come into play, and we will all try to involve you and use this Visual Studio Code. We'll come back to Visual Studio Code. We have announced it on the documentation. There's this part where we set up some requirements for this session. So if you haven't yet installed Visual Studio to attend the hands-on section, it would be nice to have Visual Studio Code installed, and then we will use this live share extension to work together on a solution. But we will come to this later. So that's the general agenda. So as I said, we are going to do this workshop based on Python, but we will be interested in what's your favorite language. So maybe you can join this Slido session. Dylan, can you paste the link into the chat to the Slido session if it hasn't been yet? It should be there.
1 second, and here it is. Okay.
Here it is. So maybe you can attend and tell us a little bit about your favorite programming language. And I will try to put it also on the screen so that we can see the results. So
it's a good answer. It depends.
It depends. Yes.
Yeah, always right.
It depends, yeah, of course. I should have added this one. Sören, pick this, put this on a note. We will add it depends to it next time.
All right.
Okay, we can see that Slido works. That's good news. And yes, actually, there is a lot of people also using C++, but Python seems to be a good choice for today.
Seems like we picked the right language.
Yes. So again, it's not our main language. It's C++, and you will see that we have kind of a maybe different style, not the usual way of using Python, but we will mention this at the correct place. Okay, there's another question I'd like you to ask, and that is what you think, how experienced you are. Sören, can you reset the chat or switch or reset it? Yes, please. With the Slido. Yeah. Okay, I guess this is a hard question to answer, but just roughly, what do you think? Do you have some experience, or do you feel comfortable at programming? Are you even an expert? So all of you have, or most of you have at least a little, or most of you have quite a lot of experience, I would say, and some only have a little experience. So we will see. There is parts that we could skip in this workshop, but we will see. Okay, so thanks for sharing this. Let's get back to the slides. As we are, at least virtually, in the UK today, I'd like to start with this gentleman here, Alan Turing, at the age of 16. And later in his life, in his career, Alan Turing probably became the first, at least one of the first scientists who actually wrote programs in order to do his research. And although pretty early in the history of scientific computing, Alan Turing already made an important statement in 1947 in a lecture to the London Mathematical Society, where he said that one of our difficulties will be the maintenance of an appropriate discipline so that we do not lose track of what we are doing. And I think that he could pretty much foresee the future really well, because at least from my perspective, and maybe you agree, to some sense, from time to time at least, we somehow lose track of what we're doing. What do I mean by that? For example, we publish results that later on we find out are wrong, and we have to retract our papers that we published. Or maybe some of our published results cannot be reproduced, even not by us. Or maybe we are using some source code that some colleague has written during his PhD, and now he left. And we can still use his code, but no one really understands his code anymore. And even every time we touch it, it somehow breaks. So the only chance we have is to rewrite everything. And probably all of this has somehow to do with the quality of the code. And I think one of the reasons for this somehow is that we, as a community of research software engineers, scientists who write code, we haven't yet agreed upon a set of disciplines that assures the quality of our code. Our software engineering discipline is not yet a profession, and even the software engineering community itself is not a profession in the traditional sense, that there is standards and rules to assure the quality of our products. But in the meantime, there have been a lot of learnings, a lot of experiences. Also, the software engineering community has made a lot of experiences that we can maybe make use of in order to increase the quality of our code and thereby also increasing the quality of our research. So better software, better research might be the topic of today. And you know that you are at the right place today when somehow this looks familiar to you. Maybe you have already experienced this situation when a colleague came into your office and asked you to show the feature that you have been working on last week that you told about in a meeting. So he's eager to see this, and of course you were happy to show him. Your IDE is already open, you have been working on something else, and you fire it up, you start the application, you press a button, and it crashes. So yesterday it worked. So what happened? You have been working on something else, and while you were working on something here, something down there broke. So what's so complicated about software? Why is it so hard to write software of good quality that doesn't break? The main reason is the complexity. There is a lot of complexity. Frederick P. Brooks divides the complexity in an essential part and accidental complexity. And the essential complexity comes from the scientific problem itself that we try to solve. And of course, it's science, and there's a lot of complexity that we need to solve. And programming is the art of managing and organizing complexity. And in addition to this essential complexity that we cannot get rid of in any case because it's inherent to the problem, in addition, there is a lot of other complexity. You have to manage your programming language. You have to manage the compiler. You have to manage your IDE, your source code management system, the HPC cluster somehow. Nowadays, there's graphics cards in this HPC systems that you somehow have to use. There is network communication involved. You have to somehow do post-processing of your results. All this adds additional complexity, and somehow we have to manage this complexity. And here's a diagram that I will come to, that I will show frequently. And this shows the level of complexity that on which we can address the complexity itself. Ideally, we have an application that already handles all the complexity for us. Grady Booch says the function of good software is to make the complex appear to be simple. That means that the application hides all the complexity from us, but somehow internally it's managed for us. But we are here today because most of the time there is no such application that we can simply use in order to solve the problem. So there is other levels that we can make use of. Alan Turing, he wrote his application directly using binary. He talks to the computer itself on the lowest level, but there is also levels in between. As a Python programmer, you're probably used to use libraries that provide a certain functionality for you that you don't have to deal with yourself, that you can use. So you can also then work on this level then. But maybe there is no such libraries. Maybe we have to also build our own functions to address all the complexity. And there is other levels and other methods in order to reduce the complexity and rise the level of abstraction. And that's what we are looking at today. We will talk about object-oriented programming. We will talk about principles that are based on object-oriented programming, and then design patterns which sit slightly above those levels and make use of those practices, but a little bit more specific, but not or provide not the same functionality, not on the same level as libraries or frameworks, or so to speak. Okay, so one other aspect we are going to talk about, and what also makes software hard to deal with or hard to build, is that software isn't bound by the laws of physics. Software provides the ultimate flexibility. If you can think of it, you can build it. And this flexibility somehow is a burden also, because there is many ways on which you can achieve your goals. There's many different ways which you can go. And the problem is that you as a developer, you have to decide which way to go. And the problem of making a decision is not that you decide for something, but with the decision for a way you go, you decide against all the others. You close the door, probably. And that's nothing that you want to do, because in software, you want to stay flexible and you don't want to close this door. So one aspect that we can take with us as a learning is that we will try to postpone decision as long as possible. Because the longer we postpone a decision that we make, the more information we have about our problem, about our software, and the better is the decision that we make. So because it's based on more information that we have. And then we will try to make decisions that don't close all the other doors, but keep them open so that we can stay flexible. And one aspect, and that's one of the most important things that should take from today, if there is one thing, then it would be this, that in order to make the decisions, an aspect we have to consider is the dependencies. What do I mean by that? We have looked at this example. When someone changes something here, something down there breaks. Why is that? It's because these parts in the application, they are somehow connected with each other. They work together with each other. And these connections between the objects builds up dependency, strong relationships. And this makes the software breaking. We will look at this aspect in very detail later on, but we should keep in mind that whenever we have to make decisions, we should consider the dependencies. And I think it will be clearer, will get clearer during the talk what I mean by that, but keep this in mind. So that's roughly the agenda. One large part is that we need to address and manage the complexity somehow, and then we will have to consider making decisions in one or the other ways, and we will always have a look at the dependencies by this. So why are we here in the first place? Our society is more and more based on software, and so is our research. I have put a slide up here with a diagram from Simon Hattrick from the Software Sustainability Institute. And this diagram is from, or the survey is from 2017. There's probably new data, but it pretty much covers the point that I like to make. That is that 2/3 of all publications in 1917 already had a relation to software. And if we look more detailed into this survey, this is also data from them, from the Software Sustainability Institute, then 90% or more than 90% of all academics say that they use software for their research. And this could be any software, which is shown here on the right side. Could be Python, could be R, but it could also be Excel or MATLAB or Word or something, any software. And 70% say that their research wouldn't even be possible without the software. And now comes the important part. and that is us, that is this 56% of the developers who actually write their own software in order to do their research. What kind of people is this? This is us. This is the scientific programmer. It's not by accident that I put up male here, because 70% nowadays are still male people, 30% female, but it doesn't matter. Most of them have a master's degree or even a PhD, or trying to achieve a PhD. What I mean by that is that they are usually smart people who don't have a hard time learning a programming language. At least they prefer learning a programming language over explaining their complex domain-specific problems to software engineers who then develop a solution for them, apart from not having the money to pay those people, but still they would prefer this. But on the other hand side, most of them are self-taught programmers. And that's fine. They don't have formal education in engineering or software engineering. And another aspect is that, and that's maybe part of the problem, is that most of them don't identify themselves as software engineers. And the reason for this is that software for them is only a tool to produce results which then can be published in papers. So they get the reputation for the results, not for the software itself. So for them, or for us as a community, software is not a first-class citizen. And I think this is something that needs to change, and the progress has already started, that we get more reputation for our software. And I think this is a good process. We need to drive this forward, because our expectations from our software are rising and rising. And that means that the complexity of our software is increasing continuously. And the reason for that is Moore's law. I'm sure you have heard of Moore's law, which says that the floating point performance of our hardware, of our computers, is doubling roughly every 18 to 24 months. And this increase of performance has resulted in 6 orders of magnitude of price performance drop in the costs of floating point costs. And that means that with this increasing of floating point performance, also our expectations towards our software are rising. And that means that the bar is rising higher and higher. The low-hanging fruits are long gone. Nowadays, we have to solve complex multiphysics problems. We have to combine and integrate codes from different groups. The lifespan of our software is getting longer and longer. It's not possible anymore within one PhD period to solve or build a complete scientific application on your own. You have to base your work on the work of others. That means that the work needs to be, or the code needs to be well documented, well written, so that everybody can understand it and base their work upon the work of the others. So now the question is, why is this so complicated? I told you that there is this, never since civilization existed, we have seen a technology like computers which have gained 6 orders of magnitude of increase in this performance. And the problem is that the technology, the methods, the techniques to create software couldn't stand this development. The increase is by far not so much. And that's not because the development of these technologies is so slow, but the development of this floating point peak performances is so huge. What do I mean by this? I mean that the tools that we have, the paradigms to address the complexity of the problems with our programming languages is from the 1960s in general. 1958, John McCarthy developed Lisp, the first functional programming language. And Lisp is still there, and so is the paradigm of functional programming. Python has parts of functional programming paradigm. The other programming paradigm that we usually use is object-oriented programming. Ole Johan Dahl and Kristen Nygaard, they developed a Simula 67 in 1966, and with this came the paradigm of object-oriented programming. 1968, Edsger Dijkstra published a very famous paper, Go to Considered Harmful, and with this came the structured programming approach. So of course, the tools, the programming language, they have become more modern and all this evolved, but the paradigms are still the same. And I'm of the opinion that we have to use these paradigms in the best efficient way in order to address the complexity of our programs. And that means that we have to know those tools really well. And it's worth spending more time of our work learning and mastering those paradigms in order to increase the quality of our code. Because, as we will see, it will make our work more easier for us. The reality is that although the performance has gained a lot of increase over time, the time to solution didn't decrease, but still increased. And one of the main reasons is that we spent, according to surveys, we spent 50% of our time finding bugs. And part of the reason is the quality of our codes. And I've put up a diagram here, which is from Martin Fowler. He calls it the design stamina hypothesis. And what this graph shows is the number of functions over time, the cumulative functionality over time. And there's two graphs, the blue graph and the red one. The blue graph is with not so good design, let's keep it that way, not saying bad design or no design at all, and the red graph is good design. And because people get reputation for the results and not so much about their software, what we do is we strive for early results. We try to get results as early as possible so that we can publish them. And that this might end up in kind of a quick and dirty approach. So most of our software tend to follow the blue graph. And going quick and dirty in the beginning turns out to get a good increase, but then over time, the velocity decreases, the graph flattens down. Because when you go this quick and dirty approach where you don't focus too much on the quality, you make a trade-off. You might say, okay, I'll fix this later. Let's get the results and then fix this tomorrow. But the truth is you will never fix it tomorrow. You don't come back and clean up your code. And doing this builds up what Ward Cunningham calls technical debt. And at some day you will have to pay back. And this technical debt will lead to this decrease of velocity, so that someday you will not be able to add any functionality anymore without breaking your code. And then comes the day when it's time for version 2.0. You have to start over again. You start from scratch now, reaching out to make it better. But in reality, that most people who created the software in the first place are not there anymore. All the experience is gone. You start over from scratch. Great men think alike. You do the same mistakes and you end up with the same situation if you don't focus on the quality of your code. Because the red graph, if you use the red graph, you might start a little bit slower, but in the end, it pays out that you focus on the quality. Now you might argue, you might argument that why not first go the blue graph, the blue way, and then here at this point, switch over to the red graph. The problem is that you will never know when you reach this point. So the only chance you have is to start with good design in the beginning. And Robert C. Martin, a guy that I will quote frequently, he summarizes it and says that the only way to go fast is to go well. In addition to this productivity crisis, there's also this credibility crisis. We talked about it in the beginning. The results of our software are sometimes questionable. Of course, we can all validate our software and verify it at some time, but most of us don't have tests that make sure that when we change it, that the software still produces correct results. I wouldn't trust it. So there is kind of questionable reliability in our software. Also, the reproducibility is questionable. Nature has made a survey under scientists in general and asked them, and they were of the opinion, or 90% of those scientists were of the opinion that we have kind of a reproducibility crisis. And this is nothing new. It has been there since the early days. And in the early days, the software developer typically was a scientist. We were all like Alan Turing, scientists who wrote software in order to do their research. Up until 1968, where the NATO held a conference actually in Germany, in Garmisch-Partenkirchen, because they were of the opinion, while it might be tolerable to have this questionable quality of code in science, it's all in all not tolerable to have this kind of software in mission-critical military software, because this might cause, in the best case, to lose a lot of money, but in the worst case, actually cost life. So they decided to establish a new discipline which was called software engineering. And this discipline name was by intention, because engineering implies that it's a profession. And professionals care about the quality of their software. So they wanted to establish standards and rules and a discipline that focuses on the quality of software. And since then, both disciplines have somehow lived separately from each other. But in the meantime, the software engineering discipline has made a lot of experiences and a lot of findings in order to increase the quality of software. And all this is already there. They have published their experiences, their results, they have written books. And I think it's time that we reunite the forces and we take some of their learnings in order to increase the quality of our code, because we have a growing social responsibility. People trust our results. During COVID-19, during the climate change, all this may also have impacts on our society, and we need to increase the quality of our code so that we can trust it. And one way to start with is to care more about our code, make the code first-class citizen. Again, it already has been started, but I just want to underline the importance of this development. And Robert C. Martin, the one I already mentioned, he has written a very good book, which is called Clean Code. With clean code, he means code that is of good quality. And he has asked valuable professionals what they think clean code is. And Michael Feathers is one of those who is mentioned in the book. And he says that clean code always looks like it was written by someone who cares. So again, we should start caring about our code, because if we don't care about our code, there is something which is called software entropy that happens. Software also targets towards chaos, and it's comparable to the broken window effect. Maybe you have heard of this. Consider you park a car with a broken window somewhere down in a large capital. I think it was done in the survey was done in New York. If you park a car down there and come back a couple of months later, your car might look like this. And same is true for buildings. If you have a building with a smashed window, it looks like no one cares. And if no one cares, why should you care? Why not smash another window? And same is true for your code. If you're working on your code with your colleagues and your colleagues don't care and the code looks ugly, why should you care and not doing a quick hack to get the results early? Why should you care about the quality? And yes, so it's time to start caring. So yeah.
Sorry, but we have a question in the Q&A. Maybe we can discuss it in between.
Of course.
The question is there a case for quick and dirty in generating prototypes to get buy-in for further work?
So prototype, we don't have Yannis here today. I'm not sure if I understand the question correctly, but of course, prototypes are of high value. Prototyping is very good to find out if a solution in general works. It's like risk management. You first check if it works in general, but then going to the production solution implies that you throw away the prototype and start from scratch, and that's what people usually not do. People say, okay, it's already working. We show that it works. Let's build upon the prototype. And then all this quick and dirty code becomes all of a sudden what we call production code. So it's not there's nothing to say against prototyping, but the important part is then to start from scratch and make it right, or at least clean up the prototype intensively. Is this an answer to the question?
Yes.
Yeah, okay, so can I continue? Yeah, okay, thanks. I'm sorry, I haven't the chat open here because there were so many windows. But yeah, thanks for interrupting me. And again, is there other questions? Since we stopped, maybe we can look at other questions. I can open up the chat here, maybe. Is this in the Slido chat or in the Zoom chat, the question?
This question was in the Slido, but there's no other.
No other question. Yeah. Okay, then if you have questions, feel free to ask them in the Slido chat, and Sören then interrupts me, or just unmute and ask a question. Okay, so we have this broken window effect, and we need to start caring. And what Robert C. Martin suggests is that we should follow the Boy Scout rules. Boy Scouts have the rule that they always leave the campground cleaner than they found it. And we could also apply this, and he's asking us to also apply this in our source code. Whenever you check out the code, clean it up a little bit, fix the indentation, split up functions, large functions, into smaller functions that are easier to grasp in order to reduce the complexity, or find better names for variables which are not expressive at all. Just clean it up a little bit and then check it back in, or clean it up before you check it back in. There is a lot of good ways mentioned in the books. There's nice chapters that are easy to read separately from each other. You don't have to read the whole book, but there's a lot of value in this book. I highly recommend this book, which is more targeted towards the source code level, so to speak, how to split up functions and clean up your code and make it look better and easier to understand. Not so much on the conceptual level, but more on the code level itself. But today we are going to focus more the conceptual level of our software. And software engineering in that sense has a lot in common with literature. Here's Joan K. Rowling, one of your famous authors, and she's obviously a very successful author. And she knows at least one language really well. I guess it's English, because I think originally Harry Potter was written in English. But Harry Potter works as well in German, Spanish, or Russian. On the other hand side, knowing this language, English, doesn't make her a successful author. And the same is true for our software development discipline. We all know at least one language, Python, C++, Ruby. But knowing this language doesn't make us a successful software engineer. There's more to be a successful software engineer. On the other hand side, the concepts that we use to create the software are the same. In general, it's object-oriented programming. And object-oriented programming itself is language agnostic. It doesn't matter if you write your software in Python, Ruby, or C++ on the conceptual level. Of course, there's differences, as with human languages. Some jokes work better in English. You cannot directly translate them into German, and they are simply not funny anymore. And there is benefits of certain programming languages, and there is drawbacks. But the concepts in general are the same. So what makes a successful author? Of course, we all know that in Harry Potter, there's a main character, and then there is maybe a little love story to have something for your heart, and then to make it a little bit more exciting, there has to be a murderer or something like this, or a thief, something exciting. But the important part is to combine all these characters, all these aspects, all these facts. The storytelling, the plot is really important, the connections between the characters, the little nitty-gritty inside. It's not so much important that you know how to create a main character, the details of the character, but how to place them in the story. And the same is true for software. It's easy to find an implementation of the quicksort algorithm. Probably you can Google it in any language, and then you can copy and paste the code into your IDE. But the important part is that you know where to place it and how to connect it with all the other parts in your application. Simple example, simple story is a joke. Probably a joke has only a little facts to know, but the important part is how to structure it, how to explain the joke, or how to tell the joke in which order in order to make it funny. If you mess this up, it's not funny anymore. So how do you learn this? Probably you learn it the same way as you learn how to write novels. By one aspect is reading novels of others. Reading the story of others, reading a lot, reading the source code of others. And then you have to do it. It's practice. Software engineering is hard practice. So with this comes the experience. So the question now is, how can we estimate the quality? Not the quality of a novel, but the quality of our code. There has been done a lot of work. There's been identified many quality aspects, and McCall categorized those into two parts. he said that there is external quality factors and there is internal quality factors. The external quality factors address the needs of the users, but the key to achieve this external quality is the internal factors, which are the needs of the developers. And I'm not going too much into details of these aspects. I guess if you read them, they're pretty obvious. Of course, software should be correct, it should be efficient, it should be robust. It's obvious from the user's point of view. And the internal quality factors, it should be readable, it should be testable, it should be portable. So you should be able to reuse parts of your application in other parts. You can go through this afterwards, and be flexible and maintainable. And is it Jeffrey Carver? He made a survey in 2007 where he asked scientists, software or research software scientists, I don't know if the name was already there then, but scientists who write software, and he asked those, what do they think is the most valuable quality factor of research code? And they said that it's, on the one hand, it's functional correctness, it's the performance. Actually, most people might have been from the HPC community. Portability, so it should be able to run on any machine. It's very a challenge on HPC systems to run your code there sometimes. And then the maintainability. Now, the question to you is, what do you think is the most valuable quality factor of research software? Try to show the link should be still valid, the link that you have. So question to you, maybe you can post it again, Sven or Sören, that we can see what you value the most. So functional correctness. So functional correctness. Second, maintainability of functional correctness. Okay. Okay. So I don't think that there is a right or wrong answer. So let's keep it that way for a moment. And I also tried to answer this question, but I will take a slightly different view on software. I will take the view of Jack Reeves, who compared, in one of his papers, he compared the engineering product and the costs for engineering products with the costs for its design. And I'm from the civil engineering discipline. That's why I put up a house here and a construction plan. So in civil engineering, we spend a reasonable amount of time and money on our design phase, thinking about every single detail to create construction plans from which we then build the actual product, which is, for example, a house or a bridge. So why does this make sense? It makes sense because the product is really expensive. Think about building a bridge. We start from both sides, and then in the end, we have to fit precisely together, because if it doesn't fit, it would really cost a lot of money to make the correct adjustments. So in order to not have to spend this additional money, it's worth investing a lot of brain power in thinking about every single detail. And the same is probably true when you decide to build a house for your family. What you do then is that you find an architect, at least that's what we do in Germany. We go look for an architect, and then we spend a reasonable amount of money, I don't know, for him, because we trust him that we can tell him about our dream house, how we think our dream house should look like, and then he picks up all these ideas from us and creates this dream house, at least on paper. But in the end, usually what you end up with doing this process is not 100% your dream house. What do I mean by that? Usually it's only 90%. Because when you then enter the house, you find out that when you open the front door collides with the bathroom door, if this is also open. So it would have been better to open the door to the other side, for example. Or you find out that in wintertime, there's not so much sun, so it would have been better to have the window a little bit larger, so to let the more sun inside, or another window on the other side to get more sun into the living room. Or from our experience, maybe you have an oven in your living room and there's a little hole in the chimney that from time to time, every 3 years, someone needs to open this little hole and clean the chimney. And it turns out that exactly at this position, there is this bookshelf that you placed there originally, and you have to take down all the books in order to open this chimney and clean it. So although we built a lot of houses, it's still not possible to think about every single detail in the first place. And that's why we, in this process, usually end up only with 90% of the best solution. But still it's a success because the construction company says, that's the plans. We build it according to your plans. So it's a perfect result, although only 90% of what the customer actually wanted. Now let's do an experiment in mind. Same example, you want to build your dream house, but the difference is building the house costs only £100 and is done within 1.5 hours. Would you then go ahead and ask an architect and pay him a reasonable amount, £20,000, in order to do this planning up front? Or would you do it maybe yourself, draw a quick sketch on a napkin and hand it over to the construction company, pay them £100, wait 1.5 hours, and then have your house built so that you can walk into it, look at every single detail. Of course, the first iteration looks terrible. It's far from being your dream house, but there is parts that are already nice. And then you think about what needs to be changed, what needs to be adjusted. Maybe you should rotate your house a little bit to have more sun in the living room, maybe have a next window on the roof to let more sun in, maybe have the door open to another side, and then pay another £100, wait 1.5 hours and have this house built, the next iteration. And this goes on and on until someday you are ready to move in. It's not finished, it's not totally complete, but it's good enough to move in. And then you decide to get children and you need children's rooms, and then you pay another £100, wait 1.5 hours and have this children's rooms created. And then the children get older, they go to college, they move out, and then you decide to have this children's room combined together to have a billiard room or something. And pay another £100, sorry, and wait another 1.5 hours, and then have this house adjusted according to your current needs. So then probably you end up with a house which is much more according to your dream house than on this other approach. And now we keep this example in mind and we look at software. In software, the design is the source code and the product is the software itself. And the product is created using a compiler. And while in the early days, computing hardware to run the compiler was really expensive compared to the personal cost, to the costs of the developer. Nowadays, computing simply costs nothing. So the compiler runs for free, actually. And the only costs you have is to creating the source code, to build the design. So coming back to this example, it's much more like the second example where the house is really cheap compared to the costs for the design. So in software, at least nowadays, what we have is this iterative approach, this incremental approach in building this software in steps. Only do a little design, build some part of the software, look at it, and then refine it according to our needs. In the early days, Winston Royce published a paper from which came the Waterfall Approach. This Waterfall Approach works perfectly when the costs of the product are really expensive, when running the compiler is expensive and the cost for the people, for the developers is really cheap. That's what the situation was in the early days. So they followed this traditional approach, which was perfectly reasonable because we do this approach in every other engineering discipline. But nowadays, we have this agile approach. That's where agile comes from. And this agile approach is perfectly reasonable for us because it's possible to react to these changing requirements. And that's what we have in science a lot. We have no fixed set of requirements. It's science. We don't know where we're going to end. So we have to change it a lot. And maybe our software is living for a very long time. So technology also changes. Nowadays, we have to do GPU computing because there is no large HPC system anymore, which doesn't have GPUs to get all this peak performance from. So we have to be able to react to according to this changing environment. And that's what agile is good for. React to changing requirements. And now coming back to the question in the first place, functional correctness, you said, is most important. But my question is, when is your software functioning correct? The requirements are changing constantly. So the moment your software does exactly what it's supposed to do is only a fraction of the time, because next time you want to change it and it does not do anything, or it doesn't do what it's supposed to do anymore because the requirements changed. So from my perspective, the most important aspect for software to be easy, to survive, is to be easy to change. And when you think about it, it's already in the name. Software is supposed to be easy to change. And the rest of our talk, of our workshop, we will focus on how we can achieve this, that the software is easy to change. Here is an example what you end up with in terms of building houses if a house is not easy to change. There's been done a lot of changes, but in the end it really looks crappy. And there's similar constructions in software. So the question is, what makes a software easy to change? Or in the opposite, it's much easier to say, to prove the opposite. What makes a software hard to change? To answer this, we will have a look at how object-oriented programming actually is working. Alan Kay coined the term object-oriented programming. And later on, he said he would have been better off not calling it object-oriented programming, but message-oriented programming. And that's the important part, the messages. If we have some classes here, but this is some kind of UML diagram that we have here, and in relation to reality, we have a person here. Sorry, it's all again a male person, but we have a car here and we have an engine. And we tell the person to move. We send it the message to move. And what happens nowadays is that the person sits into a car and drives to this place where it needs to be. And what happens on the detail level is that we tell the person to move, then the person tells the car to accelerate, and the car tells the engine to rotate. And from this combination comes knowledge. In order for the car to tell the engine that it needs to rotate, the car needs to know that there is an engine and that this engine understands the message rotate. By the way, in the end, rotate is a method that is implemented in engine. And from this knowledge comes expectations. A car expects an engine to be there and expects the engine to have the message and understand the message rotate. Same is true for the person. The person expects to have a car, and this car has to understand this message accelerate. And this builds a dependency. The car is dependent on the engine and on the fact that this implements this rotate method. Other example is this one. We have a module on top, which could be a class, and this module is the main module. Every application has a starting point. The entry point of the application, everybody knows this is main, that's why it's called main. And then we have lower level module or high level modules below main, and below the high level modules as mid level modules, and then there's low level modules. That's what this abbreviation means: high level, mid level, and low level. And the main module talks to the high level module. That's the flow of control. It sends messages to the high level module. This one sends messages to the mid level modules, and so on and so forth. And from this messages comes the dependency. So the main module expects the high level module to understand certain messages, and that is why it's depending on the high level module. And same is true for the high level module and the mid level module. So we have already understood this, I guess. So now what's the problem? The problem is that when this low-level module here changes, for example, a method parameter name changed or something, the method name itself changed. What this means is that because of the depending mid-level module, it expects a message in a certain format to be there. And if this changes, this change also affects the mid-level module. And when the mid-level module has to change, this affects the high-level module. So this high-level module needs to be changed. And this high-level module has also a depending class, which is the main class, and this also has to change. So what's the problem about change, you ask, probably. Every time you need to do a change, you probably, because we are all humans, you put the system under the risk of breaking it, because when you change something, you make mistakes. That's human. So the problem is you have to do the change, which takes time, and then the risk of breaking it. So we will find out during this workshop, we will find out how we can reduce the effect of making a change down here so that it doesn't affect all the other modules. And they also need to change when the low-level module changes. So the take-home message is, for the moment, is that your task of a developer is to design your software in order that it's easy to change, because you will have to change it a lot because of the changing requirements in science. And the way to do it is by managing the dependencies. And we will further find out how to do this, but the way to do it is look at the dependencies. That's what I said in the beginning, that we will always focus on the dependencies, because the dependencies are what makes software inflexible. not only that, also some other negative aspects, but for being flexible, we have to focus on the dependencies. Another aspect, which is also mentioned by Larry Constantine, who also first published the aspect of dependency. He also published in the same paper something about cohesion. So same example, and let's think about having, for example, some logic for printing. What you could do is you could spread this logic for printing over all the modules. Every single module has its own logic for printing parts of it. What now happens is this could work out fine. Maybe it works fine, so there's no need to change it or do something else, as long as you don't have to change the printing logic. As long as the printing logic doesn't change, it doesn't have any impact on your application. But when it does, when your printing logic changes, you will have to touch every single module. And again, if you touch it, you put it under the risk of breaking it. So what you should then do is collect all this logic and put it into a single module, which is, in the sense, very cohesive. All aspects related to printing are consolidated into a single module, is what we call then high cohesion. And then when you then have to change something, you only have to go to one module to make the change and not to every module. Of course, we still have then this dependency, and then this high-level module would be influenced, but this change doesn't spread over all the module, but so it's much more local. Dependencies and cohesion are actually metrics which you can use in an automated fashion in order to evaluate the quality of your code. And what you would end up with is, I think you already figured out, high cohesion and low coupling. Having high cohesion and low coupling is a requirement for good software. On the other hand side, if you have high cohesion and low coupling, it doesn't automatically mean that you have high quality software. There's other aspects. So these metrics work in one way, not the opposite. So if you have high coupling and low cohesion, this is what these metrics can show you. Your software, the quality of your software is not good. The other thing, the opposite, is not true. Not automatically true. So we can use these metrics to say something or find out if actually the quality of our code is bad. The same works with the quality factors that we looked before. If we invert those, it's much easier to prove something being, or to show that something's wrong, then it's easier to show that something's wrong than it is to prove that it's right. It's not like math, it's more like science. You can prove it being, or show that it's wrong, but you cannot prove it being right. But so in the beginning, we looked at the flexibility, and the opposite of flexibility is rigidity. So if a software is difficult to change, this is something that you can easily find out. This is a symptom of bad design. If your software turns out to be very rigid or inflexible. Also, it's easy to find out that your software is fragile. So when you change something and something on the other end breaks, easy to find out. And again, the reason is the dependencies. Inflexible because of the dependencies, fragile because of the dependencies, immobile. So when parts of when you want to reuse printing, for example, and printing depends on a lot of other modules, so that you have to take all the other modules together with the printing to your other application, then it's immobile. Also, again, of the dependencies. When it's difficult to do the right thing, when it's easier to do a quick hack, then it's viscous. Also, dependencies. Needless complexity. That's another aspect which is a little bit more complicated to explain at this place, but I'll try, give it a try. We will learn how to make our software easy to change, make it flexible. It has to do with dependencies. But making your software easy to change also introduces some complexity. That's because we don't want to do everything in our application easy to change, because this introduces a lot of complexity. And maybe these parts don't change. They don't have to be easy to change because it never changes. And we will find out, we have this iterative approach, and this iterative approach, this agile way of doing building, growing software, shows us the change will happen. We don't have to anticipate the future. And you shouldn't anticipate the future. You shouldn't think about what might be easy to change. Don't do this. Simply wait for the change to happen. And then if it is not easy to change, then make it easy to change. But don't make the mistake and make everything easy to change, because this, as I said, introduces additional complexity, which isn't worth it because some parts might not change actually. So that is then called needless complexity or over-design. Needless repetition is copy-paste development. If you have redundant code that looks exactly the same, and when you have to change this code, you have to change it twice or even more. And even worse, maybe there is code that looks quite the same, but there is just a single little detail which is different. This is a huge complexity, because you oversee easily that there is this one is -1, the other is +1, but the rest is exactly the same. So huge trap for mistakes. Opacity is that a system is hard to understand. It's simply names are not expressive. You can't understand what this code does. So that's actually ways to find out that your code is of poor quality. And another metric might be WTFs per minute in a code review. So yes. Okay, I think now it would be quite a good time to have a short break. Should we? What do you think? Not the lunch break, but maybe 15 minutes break and then go on.
Coffee break. No, I think it's a good idea. Yeah.
So I think we then continue at in your time 11:30. So roughly a little bit more than 10 minutes. Okay, then can you stop the recording for this time?
I pause it.
Okay. So I hope everybody's on board again. So that we can continue. So the question now is, how can we build software that is easy to maintain, easy to change, flexible, portable, in other words, sticks to all these quality aspects that we mentioned? The truth is that there is no silver bullet. By the way, there is this paper from Frederick P. Brooks, which is highly recommended. It's called Silver Bullet, and it's also used in his famous book, The Mythical Man Months. Also recommend this book to read. It's not so much about the practices, but more about the philosophy and all this background. So it took a lot of information for this talk from this book from Frederick P. Brooks. But he said that there is no silver bullet which leads us unfailingly from our requirements to a solution. Although in that time, when he has written the paper, object-oriented programming seemed like a silver bullet, and in that time there wasn't so much complexity, so object-oriented was of great help. And there is evidence that it's made some people who actually digested the topic really well, who are really good object-oriented programmers, that they are 10 times more productive than the average programmer. So it's worth learning all the concepts and really try to advance in this sense. I'm not saying being a better developer, but learning all these aspects to increase the productivity and make yourself your life as a developer in science a lot easier. So if there is no silver bullet, then there is also no standards, no rules that we can stick to, but there's learnings, there is heuristics, there is best practices, and as we will see, there is patterns, and we say what that is, that help us in this iterative approach of growing software. And as we already said, it's all there for us to handle the complexity of the problem itself, plus this accidental complexity. And the question is, how do humans in general approach complexity? First step that humans usually take, because they can only deal with about roughly 7 aspects in mind at a moment, they decompose their system. Divide et impera, divide and conquer. We divide the problems into chunks that we can then handle in terms of complexity. That's probably also something that you do in your code. If you have this procedural approach, you divide your problem into chunks, into methods or procedures that deal with subtasks. And from this, you can create a solution of the whole problem. If you can solve the chunks itself, then with this comes the solution of the whole problem itself. That's something that people usually do, split up their problems into parts. But the human brain is also capable of another aspect, and that's abstraction, which is also a really powerful mechanism. And this is something that we can also make use in software, as we will see. That's not so easy in terms of to follow. You have to, it's a little bit more tricky finding these abstractions, identify those. And if you have those, then you can also create hierarchies with this, structures out of these abstractions. And it turns out that these general principles of dealing with complexity can also be found in object-oriented programming. We have this modularization, divided impera. We have encapsulation, abstraction, and also hierarchy. So the first step that we will now look at is object-oriented programming in order to deal with the complexity. And Alan Kay, that I already mentioned before, he coined the term object-oriented programming, and he says that an object-oriented programming language at least should support the 3 key principles: encapsulation, inheritance, and polymorphism. And maybe it's worth looking at those. I'm pretty sure most of you already know this probably, but we will briefly look at it, and if it's too slow for you, then just speed me up, say skip or whatever, so then we can rush over it, but let's have a look at it. So first, let's look at encapsulation. And to do this, we have a simple example here. We have a class, a circle class, and this circle class has some data, has 3 attributes, x and y coordinate, and a radius. This attributes are publicly accessible. This is what in UML this little plus sign here indicates. So every caller, let's say that's me, yeah, I'm some caller, I'm some guy, and I know this circle, I know all circles, I can deal with circles, so I know what messages to send to those circles, and I have the idea of changing this radius attribute of the circles. Let's say you are all circles, and I'm tweaking around in some application, and I set this radius to -100. So the question now is, in this application, what might happen if some caller, me, sets the radius of the circles to -100? In the best case, your application crashes. And in the worst case, with this crash of the application, the whole system crashes. That's what we saw in the early days when an application crashed. Was very common that the whole system showed this blue screen. The question now is, who's to blame? What do you think? Whose fault is this? Is this the fault of the circle? That the circle allowed to be as a radius to be negative? Is this the fault of the caller? Is this the fault of both or none of them? What do you think? Again, this slide, do we have the Slido link handy already? Yeah, okay, at hand. Okay, let's see what you think. The circle, okay. So I guess you already know this principle. So yes, I would also say the circle. Okay, not all have voted yet, but yes, it's the circle who's to blame. And the reason is that by convention, an object is responsible in order to maintain its state. So what the circle class would then obviously do is say, okay, if it's my responsibility to make sure that my state is supposed to be valid, then I will seal my state from the outside access so that nobody can touch it anymore and make these attributes private, and then enable by some other mechanism, enable access, the indirect access to these attributes by having a set of messages that can instead be called in order to change the radius. For example, by scaling or translating the x and y coordinates or scaling. But this method then allows us, because it's not simply one line, but it's a message, it's a method where we can then check within the method that the radius has still a valid value. Okay, that's the first principle. The next example we have is inheritance. And in order to explain what inheritance does, let's consider an application that we write for a bird watcher. A bird watcher asks us to build an application, and he agrees that we first start with 5 animals, 5 birds: an eagle, a nightingale, a crow, a hawk, and a duck. And we agree that we start with having different look of the birds, but all fly on the same way. They all have the same flying behavior. So we sit down, we agree that we ship him a solution next week. So we sit down on Sunday evening. Actually, we skipped it the whole week because the weather was so nice. But then we recognized on Sunday evening that on Monday we agreed to ship it to him. So we sit down in a rush, we implement the look of the nightingale, and then we implement the method fly for the nightingale. So nightingale flies, okay, looks good. Okay, so next is the eagle. The eagle looks a little bit different, but flies in the same way. So what do? We copy paste the flying method to the eagle. Same we do for the duck, looks a little bit different. Still in the clipboard, paste the flying behavior of the duck. Okay, duck flies, Same for crow and hawk. Okay, we pack it in a zip file, we email it to him. Okay, done. Job done for this week. Time for whatever TV show. Okay, on Monday, the bird watcher calls and says, okay, not bad for a first shot, first iteration. We do agile development. So first iteration looks nice, but still, there is one aspect. Have you looked at the birds? They fly a little bit weird. So it's not a straight way. They fly like sinus-like curve. Doesn't make any sense. Can you look at this, please? Okay, you agree. Oh, sorry, you just looked in the code. Let's see. Okay, yeah, there has to be a minus somewhere, and it looks a little bit crappy. Okay, no problem. I'll do this. But first, weather is nice. Again, you go out surfing or something, and then in the evening, you remember, okay, we have to fix this bug and ship it to the bird watcher. So you go to the eagle, fix it. You go to the duck, fix it. You go to the nightingale, fix it. Go to the crow, fix it. Zip it, ship it. Okay, done. Next morning. Telephone rings early in the morning again. The bird watcher is at the phone. He opened what you just sent him, and he looked at the hawk. And the hawk still flies that way. So what happened? Eagle, duck, nightingale, crow, hawk. You forgot the hawk. So that's actually what happens if you do copy-paste development. You can easily miss one spot if you duplicate behavior. So one solution, I'm not saying that's the best solution, but one solution could be inheritance. So what we do is we introduce this bird base class. There is no such thing like a bird. That's why it looks like a little bit more, symbol-like. But this bird actually implements how all other birds fly. Of course, this is just version 0.01. There's supposed to be a lot of other birds to come, so copy and paste is obviously not an option. So all birds derive from the base class bird. Duck derives nightingale, hawk, and also ostrich. Ostrich cannot fly anymore, so what we can do in behavior is that we can also override inherited behavior, but still ducks and birds and hawks and eagles all fly exactly in the same way as the base class says. That's inheritance. Probably you know this. And what we need to remember is that this inheritance arrow here can be read as is a. So a nightingale is a bird, a duck is a bird. We will see this very often during this workshop. So inheritance, as I said, is one way to reduce the redundancy. What inheritance also offers us in the object-oriented programming languages is another very powerful mechanism, which is polymorphism. So what's polymorphism? I have made, excuse me for this little examples, but I have another example. Sure, every one of you has seen those anthills. When I was a kid, there were anthills everywhere. I'm not sure why they're not anymore, but we had anthills when I was young. And if you look at an anthill, what you see is obviously ants. A lot of ants. But if you look closer at the ants, what do you see? What you probably won't see, because there is only one in this ant tribe, and it's really rare to find this ant queen. I guess she's somewhere inside of the anthill. But there is ant queens. The ant queen is, in our story, really important. She takes all the responsibility and she manages the whole ant tribe. And we'll see that she has a very powerful mechanism to make it really easy for her to survive in this evolutionary world. And then there is also worker ants. They do the job. They collect food and build the anthill. There is soldier ants that protect the tribe. There's nurse ants who feed the children. And now comes the question, why is the job of organizing this anthill for the ant so easy? What mechanism does she use? She's not aware actually of the specific ant types. The ant queen only knows ants. That's what she sees. She knows ants. And for her, every ant is equal. They are all alike. They understand one and the same message that she sends out every morning. When she gets out of bed, she goes on the balcony and talks to the ant tribe. And she says, please, all you ants, please be so kind and do your job. And that's what they do. They hear the message, do your job, and then they start doing their jobs. And all react differently to one and the same message. The soldier ant protects the tribe, the nurse ant feeds the children and does what nurses do. The worker ant collects the food. So now you ask, what's so genius? Usually ant queens can get pretty old. And I know from myself, getting older, of course, I'm more experienced, but I don't have the power anymore I'm not in the 30s anymore. I can't work the whole night anymore. So still, she does such an important job of organizing all these ant tribe. Yes, because she has this way of talking to them all in the same way. Now comes the magic. This whole system is prepared for evolution. What's so brilliant about nature is that nature is not perfect. It's not perfect in the sense that when all these little ants that come to the world that are fed by the nurse ant, when they develop, when these cells divide and the chromosomes replicate, their mistakes happens. That's the brilliance about nature. It's not perfect. And when this change happens, most often the chromosomes are messed up, so this little ants can't survive in the real world. But from time to time, something magical happens in evolution. In 0.00000000001%, maybe in a trillion years, what will come out of accident will be a skydiver ant. And this skydiver ant will be able to live within the ant tribe and do its work in the ant tribe. Don't know why skydiver ants will be necessary to use, but nature knows why there should be skydiver ants in this time, in 2 trillion years or so. And then still the ant queen will be there because she's prepared for evolution. Because as long as the skydiver ant understands this one and the only message, do your job, the whole ant tribe still works perfectly without the need for the queen ant or ant queen to change. And this mechanism, I'm stressing this because it's important. We will see that this is actually one of the key principles that we will refer to later on, because the important part here is that we can split And this is the UML diagram. We have the ant queen here. And then we have the soldier ant, nurse ant, worker ant, and whatever ant, skydiver ant here. This is, we split up our solution into two parts. One is the core, the management part, the part that does all the important work, well, all the logic, the important logic of structuring our application sits in this core. That's the blue part, the ant queen. And then we have parts that are volatile, that change a lot. As we said, our applications, they change over time. But there is parts that don't change. And one of our responsibilities is to separate the part that change a lot from those parts that don't change a lot. And those parts that don't change a lot should not be changed when we have to change other parts. They shouldn't be affected. So in case of our ant queen, this ant queen hands out a contract for communication. When you want to play together with us in this tribe, you have to understand this message. And this is then written down in this contract, which is called, in this case, the interface of an ant. A typical ant has to understand this message in order to work together in this ant tribe. It doesn't say anything that you should do. And that's the opposite of inheritance, where we had this fly method. There was some logic actually. Here it just says there has to be the message implemented. And every ant implements this message according to their needs, according to what he or she does. So we are separating the what from the how. This interface simply says what has to be there, and then the other classes, the subclasses, implement how they do this. And this obviously can then be extended here without any change in this blue part, in the core. And the beauty of UML is that these arrows, and this is true for these associations as well as for the inheritance relationship, these arrows always point into the direction of the dependency. So we can easily see the dependencies when drawing this UML diagram for our solutions. And we can see that all arrows which are crossing this boundary here are pointing towards this blue part, this part that does not change. Think about having a change here in this interface. What would this mean? This would mean that all depending classes would need to also change, to adjust to this changes. So queen ant would be, the ant queen would be affected, and all the others would also be affected. If we change this message, everything needs to change. So we have to consider, and when we build our application, we have to put a lot of brain power into these interfaces, which are really important. Other example, and then we are done with polymorphism is a lamp. I have a lamp from IKEA that I bought 1998. It's one of these roundish light bulbs, and it's still there. And why is this possible that this is still there? It's because every lamp is equipped with such a socket. And this socket introduces the way of how to communicate with this lamp. The lamp itself doesn't produce any light. It needs someone who produces the light bulb. And this is the contract. This one is the contract for any light bulb to work together with this lamp. So any light bulb that has this socket, which fits into this this bulb holder, can work together with the lamp. The lamp is not interested at all in how this lighting is achieved, doesn't care. The lamp doesn't care. It just says it has to understand, this communication has to work in this certain way. And any light bulb which is capable of talking in this way of communication is fine. So in this early days of my IKEA lamp, there was the traditional lights, which were very power, had a lot of power consumption, and then came these energy-saving lamps, which took a while to glow up to full capacity. So they were pretty annoying. But then came this LED lamp, and who knows what else will come. The important part is that this lamp is ready for evolution. Human evolution, industrial evolution, not the evolution of the nature, but still something will change for sure. So again here, think about, we have the same structure. We have this lamp, which doesn't change at all. We have the light bulbs, they change, there's more to come. And now think about this interface. I'm stressing this because it's very important. If this interfaces, think about having a person touching this interface and changing something in how the connection works. It's impossible. You cannot, there will be a revolution. Trillions of IKEA lamps would have to go into the trash. It's not going to happen, never at all. Okay, so I'm stressing this because it's really important that we focus on the connection between our objects. About this, we have to focus on this communication contracts. That's what makes your architecture. Fowler says architecture is the important parts that are hard to change afterwards. We don't care about the details. We can make any change inside of this light up function here. It doesn't matter. You can make a change. It doesn't affect anything. But making a change here affects the whole system. That's what makes your architecture. Okay, questions? Sören, is there questions somewhere? Okay, so that's object-oriented programming in brief. Oh, sorry, this shouldn't be there. So next layer, above, having a little bit more, becoming a little bit more specific, but in addition, get a little bit more of abstraction, hide a little bit more of complexity, is design principles. And design principles, there's a lot out there. We are only focusing on 5, which Robert C. Martin, Uncle Bob, again, I'm quoting him, he collected in a paper. And he didn't invent them, but he wrote them together in this paper. And it's called SOLID. SOLID is an acronym of acronyms, which are the single responsibility, open close principle, list of substitution, interface segregation, dependency inversion. Who have heard of the SOLID principles? Who has heard of it? Is there chat?
We can make a poll.
We can also make a poll. Yes, no. Have you heard of SOLID principles? Is it new for you? Have you heard of them? We have this yes, no. No, okay, no, yes. Some have heard, so it's worse. Okay, so most have not heard of it, so or 50-50, so it's worth looking at them. Okay. So actually in the original article, you will never read the word solid because in the original article, the order is a little bit different. It's soldy. So this is also the order we are looking at it. And later on, Michael Feathers figured out that if you reorder it, it gives the word solid. So there is actually a book that I will recommend also later on, which is this one here. Can you see this? Agile Principles, Patterns and Practices in C#, which doesn't matter. So it's in a slide later on, just want to mention it now. I think in the book it says solid already. Okay, so let's look at the first principle, single responsibility principle. What does it mean? Robert C. Martin says that a responsibility for him is a reason to change. That means a class should have only one reason to change, a method should only have one reason to change, a module should only have one reason to change. Why is that? Think about, for example, a payroll application where you have an employee class, and an employee class has probably a method to calculate pay, a method to print the report, and a method to save it to the database. And what's unfortunate about this class is that it changes for different reasons. The calculate pay function will change if the accountants decide to change how to calculate the pay. The report function will change if someone decides that the format of the report needs to be changed, and the database or save me to the database function will change if the database administrators change the database schema. And the problem is that, as we learned, all the dependent classes would also have to change. Everybody who knows how to talk and work with an employee would have to change, although maybe he's not interested in the printing function, or although he's not interested in the save me to the database function. But still, everyone having a dependency on this class will be forced to change. So the solution is to take everything that changes for the same reason and put this as a one class, and everything that changes for a different reason, put this in a separate class. Somewhat, this is out of the traditional way of building object-oriented classes. Usually we group together methods that operate on the same data structure, and that's perfectly fine as long as they change for different reasons. Then we put them in different classes. Other example I have here, let's consider we have a rectangle class, and this rectangle class is used by two different applications. We make code reuse, we share code, and we have one application which is a computational geometry application. It's only interested in the area function. The terminal application just do some math, some geometric calculations, is interested in this area function. And then there is a more sophisticated application which also has a graphical user interface, uses Qt, for example, or GTK or whatever. And this has also then functionality to draw the rectangle on the screen. And so the rectangle provides a draw function. Now this computational geometry application, the console application, is based on this rectangle and also knows this draw function here. And at least if we are in a statically typed language like C# or C++, this is a problem, because all this graphical user interface stuff requires that this draw function is using some libraries from GTK or stuff, which is all coupled then to the rectangle. So whenever something changes in this graphical user interface part, the console application would be affected because of this coupling of the draw function to the rectangle. So that's obviously not something that we want to do. To stress it again, this rectangle function has two different reasons to change. One is because the draw function might change, which occurs quite often. The other would be that the area function changes, what doesn't happen so often. So we have one part here now. We split up the class. We didn't use inheritance, we used composition, because inheritance is even a stronger relationship between classes than an association or composition. So we made two classes here. We have the rectangle class with the draw function, and this rectangle class then gets this information it needs to draw the rectangle from the geometric rectangle. That's what we called it. And this part here is the console application, which now is independent. As you can clearly see, there's this arrow only points into this direction, which means we have this graphical user interface application here, which is depending on this class, which doesn't change frequently. It's not a problem at all. This is really stable here, and we can make now changes on this side that doesn't affect this other application anymore. Hope this is somewhat clear what I mean. And this single responsibility principle, as I said, it has a strong relationship to cohesion. We talked about cohesion. There's other principles that talk about concerns, separation of concerns, responsibility. It all addresses the same aspect. We should put together aspects of our application that belong together, which have a strong relationship with each other, and those belong together. And we should structure this. And this is also true for functions. So single responsibility principle also applies for functions. Think about, for example, think about a very long function, which is hard to grasp, 50 lines long, for example. We should then group together parts of this function that belong together and give them some not easy to understand names, for example. What you then end up with, I mean, people argue sometimes it's easier to understand a function which is 50 lines long, but sometimes you have to make changes to some part of this function that affects all the rest of it, and it's hard to understand. So it's better than to separate these parts of this long function and put them into little chunks of other functions that you end up with, which then can get very well defined names. That's in the end what I like to mention here is that when you split up your modules, your classes, and your functions into parts that are pretty narrowed down, maybe 5 to 6 lines long, then it's much easier to find a name for it. The same is true for classes. Sometimes you end up with classes who have a lot of responsibility, and the only name you can come up with is some kind of manager or coordinator, which is clearly an indication of that this class does too much. And same is true for functions. If you can't come up with a name, it's a clear indication that this class or this function simply does too much. And if you split it up into chunks of code, then it's much easier to find a name for it, because probably it's only used once. Somewhere in your code, you only use this function once, and then you can give it a really precise name. And that's what we will look at in our exercise later on. So this is the first principle now. Next one is the open-closed principle. Open-closed is a principle which was defined by Bertrand Meyer in 1988 in a wonderful book, which is one of the first early terrific books about software object-oriented programming, which is called Object-Oriented Software Construction. And there he said that a class should be open for extension, but closed for modification. And this probably now sounds familiar to you, because we already looked at the ant tribe and the example with the lamp, but think about it for a moment. Open for extension, closed for modification. What does it mean? It means that some part of our application will not be changed. And if we don't change it and we don't touch it again, we don't break it. And then we should have some other mechanism in order to add new code, not by changing old existing code. We saw this with the skydiver ant, for example. We added new code, added functionality by adding a new class, not by changing existing code. And if we don't change existing code, we don't break this. I stress this a lot. And the mechanism that we use, obviously, is polymorphism. We already saw this. And we have an example here. And here I already set this boundary, the boundary between the part of the code that changes frequently, which is the volatile part, and the part that shouldn't change frequently. But we have a violation here of the open-close principle. If we look at this application here, this application simply draws shapes. It has a shape function, and it gets a list of shapes. And then it goes through the list of shapes, and depending on its type, it calls a function, a draw function for the circle if it's a circle with the radius, or a draw function for a square if it's a square. We have the circle and the square classes here on the other side. But now what happens if we add another kind of shape, a polygon, for example, or triangle? It's obvious that we would have to make changes also on this side. So we would have to add another if statement here and then another draw function here. Now you could argue, so what? It's only this small application, but in a real world application, probably you would have situations with these if statements over and over again. Probably that you would have a function that not only draws the shape, but calculates the area or translates shapes or rotates shapes or scales shapes or whatever. Every time you would have this if statement and look at the type of the shape and call an equivalent function, and you would at every place you would have to make changes once you add another shape. And obviously this is nothing that you want to do with. And it's pretty obvious probably for you what we could do here. We don't do good object-oriented practice here. The responsibility to draw the circle is out of the class. So what we could first do to avoid having changes to or adding functions on this side, we could move this draw functions into the circle class itself. Right now, the circle class only provides information about itself. It has no behavior at all, so it looks obvious to put the behavior into the equivalent class. So draw square into the square class and the draw circle class into the circle, or circle method into the circle. And then use polymorphism in order to draw the shapes. And that's what we do. We can reduce the draw all shape functions. Now that we have the draw methods in the class itself, we can reduce the draw all shape method here to this single line. We go through all shapes and then send the message to the shape that it needs to be drawn. And now comes the part that I referred to in the beginning, where I said that we might have a kind of C++ style in writing our code. So in Python typically is a dynamically typed language, which means you don't have these explicit interfaces that we see in UML. It's by convention, so to speak. The classes implement these, what you call it in dynamically typed languages, protocols or informal interfaces, which are not written in code, but somehow has to be documented. Usually you would document those with your tests, or you would have documentation within your classes. How is it called, Sven? These doc types or doc type strings or something, where you indicate that your functions adhere to a certain kind of interface. But nowadays, what you can do, or what people do, is that and that's also what we do, we make those interfaces explicit. So we do some kind of statically typed way of doing it into this dynamically typed Python, and that's by using this abstract base classes. So I like to do this for this workshop in order to make those interfaces, this communication contracts, a little bit more expressive and explicit. And then we can use type hinting in order to make our linters support us, and our IntelliSense function in Visual Studio Code to support us with IntelliSense and all this. This is what we decided to use during this workshop. The examples in our repository will also be using having a solution using duck typing. That's what you can also call it. I think in the Rubyists call it duck types. The Pythonists call it protocols. That's also what it's called in Smalltalk, in Objective-C, the first object-oriented dynamically typed language. Smalltalk also used the name protocol, but it's important to know that it doesn't weaken the contract. The contract is simply not written down. You could also write without this explicit. It would also work without this explicit definition of the interface, but that's what we do for the workshop in order to make it more obvious for us. I think it's also a kind of documentation if you do it like this. Okay, questions?
Yeah,
so far?
We have a couple of good questions in the chat. The first one is, so if you find a more performant way to implement something, you should also keep the legacy function instead of changing it?
If you find a more performant way of doing it, which is then the legacy function, or not?
No, you have a rather non-performant function and you find a better way of implementing it. Should you keep the non-performant function, or
if you have a function which is not performant and you find a better way, why would you keep the non-performing function?
I think this is a question related to the open close principle, because you said like we don't want to change existing code.
Okay.
Yeah.
So you think, okay, now I understand the question. Okay, the answer is as follows. Probably, if you find for me, it's more like a refactoring. Okay, if you find something that can be refactored and look better, you should do it. Because if you found a way to do it better and you found the better way, it doesn't mean that it will change frequently. Having something that you or doing a change in order to increase the design and increase the performance or having better quality should always be done, no matter if it's in the core or if it's not, because probably it's only a change for one time. It's not very I think once you have improved it, you will rarely find tomorrow. You will rarely find another way of improving it even better. So maybe it's a one-time change. Okay, we are separating the parts that change frequently, or the parts, for example, when we don't know if it's when the requirements. Okay, for us the requirements are we are the people who are gathering the requirements. It's our requirements ourselves. So we probably can't trust that when something, or we can trust that when we think that it's probably not very likely that something will change very frequently, then we don't have to separate it and put it into the volatile part. But if we have parts that change frequently, those belong into the volatile part. If we have a part that is stable, but we can still increase the quality of the code, we should still do it. So you shouldn't neglect doing increasing the quality of your code just because it's on the non-volatile side. I wouldn't suggest it, but just because you do this one change doesn't mean you should take it out of this stable part and put it into the one volatile part, because it's not likely that it will change frequently. Maybe this is an answer to the question. Is it? Sven, is there a reaction?
Yeah, so we have a couple of comments, so
maybe you can unmute yourself and we can also have a discussion here.
Feel free to unmute.
And also maybe turn on your camera. Oh.
Sorry. Hello? No.
Yeah.
Yeah, sorry, two people in the same room and it echoes when I try to speak.
No problem.
So I think it's an important distinction to make between changing implementation and changing interface.
Yes.
So the principle of saying you should extend and not change should go to the interface.
Yes.
As long as you change the internals of something, you should do as you damn well please. That's the whole point of hiding stuff inside. But do not ever, ever change interfaces.
Yes.
I think that's an important distinction to make here,
Yes.
because otherwise it sounds quite conflicting the way you explained that.
Yes. So probably this is the slide where I said pretty much what you just said. Changing this interface has an effect on all the other parts of the system. There is nothing to improve here, I think, because interfaces are really narrow. There is no code in there actually which covers any behavior. It's only referring to understanding these messages, implementing these messages. There is no really behavior in there in this interface. The behavior then is all in these classes. And then it depends if it's a change which is inside a method. There is the effect it has on other classes is nearly zero. The influence on other classes is then becoming more of a topic when you change something of the public interface of the class. And public is all these methods which is indicated with this plus sign, which is all these public parts of your class form the public interface, the public API. And if you change something, for example, at the signature or the parameter, then it has an effect on all the depending classes. Data encapsulation also refers to data or to information hiding. You hide all these internal details from the outside. Everything which is inside the methods, you can, of course, change because it doesn't have any influence on your public API. But this is getting a little more detailed than the discussion, but maybe that's a good addition to the question before. There is, of course, changes that you can do to your classes which don't affect all the depending classes because it's in the details inside which are sealed from outside, which are hidden behind the public API. But still, in C++, this could mean that you have to recompile all the other parts. And then you have to consider if it's worth doing this little change, maybe just, don't know, just small changes. But if you touch a file that needs to be recompiled, header file in C++, and all the including parts then have to be recompiled. And this in large systems that could have an impact. But for sure, to increase it depends. If you change something on the interface and you see the need that you need to change something there, which is important, then you have to decide, is it worth it or not? But you have to be sure, or you can be sure that it has effects. That's what you have to be aware of, that when you change an interface, it has effects on all the other depending parts. Because an interface simply consists of the public API. It defines the public API of all, at least parts of the public API of those subtypes that are implementing this interface. Is this an answer?
Yes, that answers it. I just wanted to be said clearly in case people didn't.
Yes, thank you for pointing this out. Other questions or remarks? Maybe I wasn't clear with some things. Okay, so where do we stop? Open, close here. So, okay, so back to this example. Now we can see in this case that both parts, or at least the non-volatile part here, only depends on shape. We're not using the subtypes anymore on this side, making us independent, not depending anymore on the subtypes. So changes in these subtypes don't affect us on this side anymore. In UML, it would look like this. Yeah, again, and you see always the same structure. You know? We always have some part that communicates with some volatile part through this interface. So again, if this part changes, we have to do the changes here. If this part changes, we can also do a change here, but there is no one actually depending on this class. So you could of course do the change here. It wouldn't have any impact on these parts, but the change here is the important part. There's no arrow pointing to this class, so a change here wouldn't affect anything else other than putting it under risk of breaking it. Okay, I think we should continue. So there's Liskov, substitution, and after the solid principles, then we have the lunch break. Is this fine for you? So I think it's going to be, yeah, 15 to 20 minutes and then have lunch break. Okay. Okay, Liskov substitution. This is called by, according to Barbara Liskov. She was the first pointing out that we have abstract types, or could have something like abstract types in object-oriented programming or programming at all. And this is what this principle is referring to. It has a strong relationship to inheritance and abstract methods. So let's phrase this a little bit. If you have some caller who talks to some type and you change this type, or an object of this type, to a subtype, then the caller shouldn't be disturbed in any case. Simple example is if you are used to driving a car, you have your made your driver's license, and probably when you learned driving a car, you have probably in the UK, you probably drove a Rover or something, but you still should be able to drive what's a Rolls Royce or Jaguar. It shouldn't make a difference to you as long as all behave according to a car. But the ostrich couldn't fly. Yes, good point. There is something in a remark in the chat. It's a bad example. So this is not a good inheritance hierarchy. It's actually a violation of Liskov's substitution principle. Yes, it is. Good point. Thanks for pointing this out. Yes. So let's make an example to make this clear. The question is, as I said, we will come back to this arrow, this inheritance arrow. It is read as is a. And this, what this says is that a square is a rectangle. Question is, do you agree? Is a square a rectangle? Again, let's make a short, quick poll. Is a square a rectangle? That's the question. Yes. Okay. Square is a rectangle. Okay. Let's see. Is a square a rectangle? At least in geometry, of course, you're right. But let's have a look from the standpoint of Barbara Liskov. Is a square a rectangle? We have this rectangle class here, and a rectangle class has two attributes, height and width. So when square derives from rectangle, it derives two attributes, height and width. Okay, a square only needs one. It only has one width. So, okay, we wasted a little bit of memory, but okay, memory is cheap, doesn't matter. But then, if we look further, we find out that if a square derives from rectangle, it inherits two functions, set height and set width. Doesn't really make that much sense in terms of a square. And also, if we set the height, the widths typically don't change, but at least with a rectangle, but we can make it work. We can override the set height and the set width function so that we also set the height and the width accordingly. So if we set height, we not only change the height, but also the width. But it didn't feel right. Do you agree? That it doesn't feel right. So, but still, it works somehow. But then someone who uses the rectangle class somewhere in his code, in his core of his application, he uses the following code. It's just called foo here, but this foo function gets a rectangle as an argument here, and then it sets the width of the rectangle to 5 and the height to 4, and then makes a perfectly reasonable assumption from the standpoint of a rectangle, of someone who works with a rectangle. It's reasonable to estimate or assert that the area of this rectangle now is 20. But now, as square is a rectangle, it's also very likely that someone passes in a square. And then it doesn't work anymore. It crashes. So the guy who has written this code realizes, oh, it crashes, and he debugs it and finds out, oh, someone is passing me a square here, and I was expecting a rectangle. So now he can make it work. So one thing he could do is he could extend this if statement and check if this rectangle is actually a square, and then make something different here. It's not perfect, but I just made a quick fix here. But the problem now is that once we are mentioning here this square, we are making us depending on the derivative of the rectangle, and that is a violation of the open-close principle. Because every time we now we're depending on the base class, and then we are depending on the derivative of the base class, and that's the violation of the open-close principle. So that's not a nice solution. So apart from having this technical problem here, also a square doesn't really behave like a rectangle. It works different. And that's probably one of the problems that we have, that we read this inheritance relationship as ISA, and it should be better read as behaves like. Then it would be more obvious. So in reality, in geometry, a square is a rectangle, but it's not necessarily to correct. Okay, but it behaves like a what did I just say? Where did I left? I had an eye on the chat. So although in geometry a square is a rectangle, in code it's not always the same as in reality. In code, a square is not a rectangle. At least both have in common that they are all shapes, but a square does not behave like a rectangle. We can get more formal here on this topic. If you look up this Liskov substitution principles, there is prerequisites and post conditions and preconditions that need to be fulfilled. This is the technical part, but I hope you agree that even from the feeling, when you look at the compromises that you have to do, and then with this final example here where we force the failure, you agree that a square in code is not a rectangle. Okay, the next one is the dependency inversion principle, and the dependency inversion principle pretty much is a restatement of the open-close principle, but from a different angle. The dependency inversion principle requires that high-level modules should not depend on low-level modules. Both should depend on abstractions, these interfaces, and abstraction should not depend on details. Details should depend on abstraction. The dependency inversion principle requires this in general, but of course, as I said, we cannot always make everything flexible, everything easy to change. But we should apply this dependency inversion principle where it's necessary. And it's necessary there where we have parts that change frequently. In the parts that don't change frequently, we don't have to apply this dependency principle. Another example, and it's, as you will see, very similar to what we already saw. We have a button, and this button is controlling a lamp. Problem now is that we want to reuse the button, but the button is tightly coupled to the lamp. The button only knows how to deal with lamps. So again, what we can do is we can apply polymorphism, which is then, as we will see, inverting the dependency. In this case, the arrow points from the button to the lamp, but if we apply the dependency inversion principle, which means we make use of polymorphism, now this arrow points to the button, what we call button server, and then the lamp implements this contract, and the arrow here, the inheritance arrow, points to this button. And the button server, this interface, is placed on the same level as the button. As with the queen ant, the queen ant hands out the contract, and the one who wants to deal with the queen ant has to agree on this contract. And the same is true for the button here. That's why it's called button server. The relationship is closer to the button than to the lamp. It belongs on the same level as the button. It is part of the core of the application, which is this red rectangle. So we inverted the dependency. Prior to this, the dependency was to the lamp from the button. So the button was depending on the lamp. Now the button introduced this contract, and the lamp is depending on this contract. That's why it's called dependency inversion principle. So we inverted the dependency. Now the arrow goes in the other direction. And now back to where we were in the beginning. Now in the beginning, we had this example of having this set of modules working together with each other and having a change in the low-level module. And we saw that this change in the low-level modules propagated upwards through all the levels up until the main module. And what we can do now here is to make this change not propagating to the rest of the application, is do this dependency inversion. If we apply the dependency inversion here and introduce an interface which is handed out by the mid-level module, the mid-level modules defines the contract for the communication that then the low-level modules have to stick to, they have to implement this, then we decouple and invert the dependencies. So that when we now change the low-level module, there is no arrow pointing, okay, the flow of direction of communication is still in this direction. We communicate through this contract. So we can still communicate in the same way as before with the low-level modules, but we are not depending on it anymore. Instead we are depending on this contract here. We have to thoughtfully develop this contract, put a lot of thought into this, because we shouldn't change this. If we change this, again, we would have to this propagating changes, but this dependency inversion is the solution, so to speak. Polymorphism is the solution. Abstractions are the solution in terms of how to manage the dependencies of making, in the end, making our application easy to change, flexible in a sense. Okay, and the last one is, and then we go to the lunch break, is the interface segregation principle. And the interface segregation principle, in case of, isn't of that much of importance in case of dynamically typed languages. But if you have a statically typed language, then you commonly have the problem that you have classes who have very huge public APIs, a lot of methods that you can send, or the method that you can call on the objects. The older your application gets, the more functionality gathers in some classes. Of course, one way is then to split up the class itself. But if you refuse to this for whatever reason, because it's really cohesive in a sense, another way of doing this is then to split up the functionality in terms of interfaces, because you have different callers, class A, B, and C, all call functions, use functionality of some service, but they will all use only parts of this public API. They're only interested in parts of the functionality. But still, if other parts of the functionality change, at least in statically typed languages, you had to recompile all the others at least. In dynamically typed languages, you are only depending on the messages, on the functions that you that you're actually calling. Yeah. In statically typed languages, the compiler checks the whole set of functions. So there, it's much more important to apply this principle. So long story short, what we could do then is we split up the interface, the public API, extracted in interfaces that we split up according to the needs of the callers. One aspect here might be, if you think about this, it could be that some clients are interested in the same messages to call. But that's not a problem if you duplicate these messages in the interfaces, because the interfaces don't provide any implementation. It's just a requirement that these methods needs to be there. So it's perfectly fine to have duplications of methods in the interfaces. And with this, I'd like to put up this last slide and then go into the lunch break. This is references that I'd like to recommend to you. The first part, there's a lot of books by Uncle Bob, and all these books have in common that they have this clean in the name, in the title. The first book actually doesn't have, but it's actually one of his first books, and this is a very comprehensive book. There's every aspect in there. I highly recommend this one. If I should only recommend one of those, I would take this one. In terms of Python and Ruby, in other words, dynamically typed languages, I would also recommend this one by Sandy Metz. It's a thin book, but most of it is also in there, and it has a closer relationship to dynamically typed languages. Also goes into testing. Clean code is also very recommended, highly recommended, if you want to focus also more on the code level, how to find good names for methods, how to write comments, what's important about comments, why shouldn't you be so careless with comments. Sometimes less is more. Clean code is more about ethics than more the architectural level. I mean, there is parts of it is in all books. He always thinks in the same way. He addresses the same topics. Here it's more detailed. Here it's more abstract. And then there's Clean Agile, which focuses on the disciplines of agile development, also the same topics, but in a different context. If you want to increase the structure of your code, of existing code, and increase the quality, Martin Fowler's refactoring book is highly recommended. this is more a classic book, or also Booch's book is more a classic book about object-oriented programming. And the history of programming is really nice described in this very comprehensive book by Steve McConnell. Is also highly recommended, and there's also very nice advices in there. And with this, we could first have a look at if there's some other questions.
I think Kim has a question. No? All right.
No question from Kim. Okay, if that's not the case, should we have a 45-minute lunch break? Is this fine for you, or is 30 minutes enough? What do you think? Kind of 45 minutes, and then we start with the practical part. Plus one. Okay, so 45 minutes. It is. Sounds good. Then we meet again. In your time, it would be 2:30, right?
1:30.
1:30. Sorry, 1:30. So in our time, it's 2:30. Sorry. Our time it's let's say 1:30. So 1:35. Okay. Maybe 1:35. So, okay, thanks for being here so far. And then we meet again at 1:35. I will be here 1:30, but 1:35 is okay. Well, then we start over. We will prepare, we'll set up Visual Studio Code and everything so that you can then join. So we have 5 minutes to prepare everything for you. Okay, thank you. Okay, let's pick up. In the meantime, so welcome back. I hope you enjoyed the lunch break. In the meantime, I had a look at some of the questions, and I like to get a clear view on what I mentioned. Maybe I rushed a little bit through the dependency inversion principle in order to get to the lunch break. So the question is, why is this inverting in what sense is this inverting the dependency? And again, I'm happy to explain or try to explain it again in a little bit more detail. So in this situation, the button is directly depending on the lamp. So you can see this by this arrow here. So let's suppose for a moment that we want to reuse the button in the sense that the button should be also capable of switching on and off other devices. It doesn't make much sense at the moment, for example, to derive from lamp, because then everyone deriving from lamp would also be a lamp, and the messages here is light on, light off, which is targeted towards lamps. So the button itself could have a dependency to other devices, but then we always had to change the button whenever we add another device, for example, a TV set or a stereo set or a microwave oven, whatever. So it would be nice to have the button be able to switch on and off all the other devices. But now, for the moment, it only knows lamps. And the name also, in the method names, also implies something like switching light on and off, which is not typical for a TV set or a microwave oven. So what can we do in order to make this button not depending directly on lamps? And the answer is that we introduce, remember the ant queen. She's not aware of specific ants. Same situation would be that the ant queen now can talk to soldier ants, but she should also be possible to talk to other ants. Now the ant queen is only directly depending on soldier ants, not on this general type of ant. So we introduce this general type of ants, but this communication contract belongs rather to the ant queen than to all these subtypes of ants. It's more a requirement handed out by the ant queen, so that whenever you want to participate in this ant tribe and if you want to be part of it, the requirement is that you understand this message. And the same is what we do here. The button introduces the communication contract. That's why this button interface here is part of this non-volatile, this core, which is the part that should not change whenever we add additional devices. This is the center of our application, the part, the management part, so to speak, in the ant tribe. So this button interface belongs, or the button server interface belongs to the button. That's what the name implies here. Button indicates that there is a close relationship. Button server sounds like it belongs to the button, and that's how it is. It's the contract that belongs to the button, which you have to implement, which you have to fulfill in order to work with the button. So this dependency here, there is a dependency on this interface, of course. It's still depending on the interface, but the interface belongs to the button. It's part of the button. The button has decided what it should look like, not the lamp. The lamp has only the option to implement this interface or not. If you want to play together with the button, the only option you have is to follow the rules that the button has handed out to you and do it or not. If you want to play with the button, you have to implement this. And now the button changes it to not only switch on and off light, but also turn on and off, so the button doesn't care if it's a lamp or it's a TV set or it's a microwave oven. The button simply don't know. It only knows that the one who's talking to implements this interface, implements the contract. So the dependency now is from down here up there. So the lamp is now depending on this contract handed out by the button. That's why it's called dependency inversion. So it's the opposite around. Button is not depending on lamp, but lamp is depending on the contract that the button hands out. I hope this made things clearer now. Does it? It's okay. So another question was, I stressed this dependency topic a lot. So another question was referring to dependencies, and maybe let's make things clear when we talk about a class depends on another class. So we have two options for dependencies, and I said briefly that we favor composition over inheritance, and I tell you why. First, this composition here, which is the same in association, composition, or aggregation, doesn't matter, it's a different kind of usage of classes, so talking to other classes, depending on them in terms of knowing their language, what they speak, that knowing the messages that they understand. And class B knows from class A that it understands these public messages. This hash here with pound sign is protected, and we have also minus, which is private, which only this class can call itself, so it's not accessible from other classes. But class B has to react whenever the public interface, which is the signature of this methods, when this changes, then it has to change, also has to change. But the dependency of this class is only on C and D, because this is publicly accessible. Protected methods can only be accessed by classes that derive from the base class. And that's why an inheritance relationship is a stronger dependency, closer binding than an association or composition, as in this case, because class B also has access to the protected method. So it not only can access those methods, but it can also access the protected methods. In a dynamically typed language, you're only depending on the methods that you actually use. in the statically typed languages, the compiler, that's in a different story. Having to recompile in C++, for example, whenever you touch the header interface or the header file, and whenever this header file changes, I mean, there might be techniques to get rid of this. C# and Java somehow find out that only the publicly available classes change and don't have to rebuild everything, but still, or most often you have to at least recompile your code. But the source code dependency is, in this case, in statically typed language, on all these publicly available language methods and the private protected messages. Sorry for that. And in case of class B, it's only the publicly available messages. This doesn't mean, I mean, this means that you have to react to the change. Definitely, if something here in the if you use as class B, use method C, and method C signature changes somehow, you have to adjust to those change, no question. But even if class A changes, and I mean, by changing the internals of method C, usually you wouldn't have to react to the change. If you have tests for method C, and method C, after your refactoring, still works in the same way, which means produces, I mean, in this case, it returns void, but considering it returns some value, even you have to calculate the sum, for example, simple example, and you refactor your code, you make it more cleaner, so the algorithm inside the function is changed, and you make a mistake there, and it doesn't return the correct result anymore, then of course also class B could be affected because simply the method does something wrong. That could be also the case if you have this very local change and you have introduced your interface and you decoupled it very loosely, but still the logic simply is now wrong because you made a mistake, then it could still happen that something on the other side breaks because you return the wrong result. But this is not what we mean by dependencies. Okay. Is there other questions now? So otherwise, then we can start with the part 3. And part 3 is design patterns. So we're becoming more and more specific, we are leaving the more general part. We talked about the general principles, the key principles of object-oriented programming, and then above this applied some best practices, some principles that guide us towards low coupled code with high cohesion. And now we're getting a little bit more, even more concrete by looking at templates that have been extracted from proven working solutions from others. Most likely, when you have a problem, a design problem, someone else had this problem before. And there is, again, a similarity to civil engineering and architecture in buildings. Christopher Alexander wrote a book in 1979 about called The Timeless Way of Building, where he identified similarities of structures in architecture, similarities of style, of structure, reoccurring elements. And Eric Gamma, as one of the 4 authors of the very famous book, which is called Design Patterns, that's why it's called Design Patterns, Elements of Reusable Object-Oriented Software, highly recommended book. Eric Gamma, Richard Helm, Ralph Johnson, and John Flusitis, they are called the Gang of 4. Whenever you read Goff or the Goff book, then it's referring to this book of those 4 people. And they took this idea of reoccurring structures and applied it to software. They looked at common software solutions. which have proven to work and identified the structures, the three occurring patterns. And they, in their book, gathered 23 patterns that they categorized and described in very detail, where they describe the solution. First, they, of course, the problem itself, and then they give a solution. And then this solution includes the structure and the interaction of the elements, and then they discuss the solution also, and then they tell you which is good about this solution and which is not so good about the solution. They will look at the dependencies, and they will also provide you some code examples so that you have a good starting point. So why does it help you? Because you don't have to reinvent the wheel all the time. Every time you have a problem, someone else probably had this problem before, and it's worth looking for a solution, for example, in the design patterns book, so that you don't have to evaluate the solution yourself. You can easily grasp what's good, what's bad, and then apply this solution to your own problem. Usually it's not the way that you just take the code and then put it in your solution, like with algorithms, for example, and then use them, but it's more like a template solution, so to speak. Most of the examples are in C++, but in general, as with every object-oriented structure, it works in any language. So then you can apply this to your solution. So I already said it's not like algorithms. It's another level. It's a structural level, and this is not a one-size-fits-all solution. You usually don't take the solution as is from the book. You apply it and adjust it according to your context. So it's not like libraries or framework where you get code, but it's more like having an architectural help in designing your solution. So why is this good? First and foremost, of course, as I said, you don't have to reinvent the wheel. You have a good starting point. But what I'd like to point out here, and that's why I showed you always this level of abstraction, is that with this we can again rise the level of abstraction because we introduce a common vocabulary. Consider this example here for a moment. We have these carpenters, and they want to build drawers. And one way to discuss how to do this is on the detailed level. So the one guy says something like, well, I think we should make the joint by cutting straight down the wood and then cut back up 45 degrees and blah, blah, blah. So it's easy to get lost in this communication, and it's quite a better way of talking to someone if you could rise the level and just say, should we simply use a dovetail joint for this example, or a mitre joint? What do you think? So it's much easier in communication, and also in documenting your code and understanding your code, even for yourself. If you use the names, the terminology from which is common, which most people, so to speak, use and have agreed upon, and that's definitely what happened. When this book came out, it was people adapted it everywhere, and those terminology, those patterns, they are everywhere. Pretty sure you have heard of them too. So it's common terminology, and everyone can understand what you are referring to, and by this increasing the level of abstraction again a little bit, so that we don't have to deal with all the details. Again, it's about managing complexity, and if we could hide a huge part of the complexity, that we don't have to deal with it, the better for us. So that's one important aspect. So it's good for documentation, even if what people do is using the names in their code. So by looking at the name of the class, it's instantly clear what role this class takes in your ensemble of all your interaction with all your objects in your application. So again, the benefits here, I mentioned most of them. We have proven solution. We have help in making decisions by looking at the solutions. We have these examples to get started. It's easy to communicate with others and pass on your knowledge. In a team, you have this standardized language to raise the level of abstraction, you have standardized documentation, and it's easy to transfer the knowledge within your team, but also within the whole community. If we agree upon this terminology, every domain has its own domain-specific languages. That's also a part in this. So you can also, of course, refer to your domain-specific terminology, but in terms of software, there's something similar. So when we agree upon this, it's also easier for others to pick other than people in your group to pick up your code from GitHub or something and continue working on it. So there's different kind of patterns, some referring to the structure of your code, some referring to creation of your objects. It sounds simple, creating object, but it's actually more difficult, as we will see, more difficult as you think. And then behavioral patterns, it's also what we look at today. So the interaction is the important part. That's what we already saw. Interaction requires dependencies, hopefully weak dependencies, so that we can have some interaction. So the question I have for you, I don't know why this is messed up here. It should be there. Sorry. This is a question I like to start with. And the question is, if you see these two lines here, these two lines of code, what do you think? Consider this two lines of code within your application core, the core that is supposed to be non-volatile. Consider these two lines be in there. One line is creating a list of strings. The other one is creating a circle with some origin, X and Y coordinate. And a hint is that the circle class, it changes frequently. So it might be a hint for you. The question is, which of the lines is a dependency inversion principle violation? Line A, line B, both, or none of them? What do you think? So there's not everyone on board again. Sören, can you send the link to the Slido again? Okay. So not sure would also have been an option, but so 7 actually attended, 8. So the answer is not so easy, I would say, but let's have a look at it. I said that the circle class is subject of frequent change. So creating this circle, making you dependent on this circle class, at least in a statically typed language, would require any change to the circle class, the effect that at least you have to recompile your code. In Python, it's always a little bit different because of this weakly typed manner, but still, I would consider this a violation of the dependency inversion principle, at least when you also call then functions directly on this class in the following. So then you would make yourself depending on this class directly. So this would be considered a violation of the dependency inversion principle. Things are a little bit different here. What do you guess might be different here? The difference is that we are using concrete classes directly. We are using strings, this the type string here, and we are using the type list from the Python libraries. But those are most likely not changing in the near future, at least not during the time we are working on this. So there won't be frequent changes. So there's no problem in directly depending on them, because there's no change that would affect our application core, so to speak. So it's not bad to directly depend on them, because we would then have direct dependencies on these classes, but as long as they don't change, the change wouldn't affect us. So from my point of view, it would be answer which of the following, it would be B. Circle is a violation, A is not. Okay, and this would be now, we should remember this, because this is a question that we will address now in the interactive part. And with the interactive part, I would like to invite you to join. If you did not already join in here, you don't have to, but if you like to also help us developing the application further, so then you can join now. Sven, send again the link to the chat if you have Visual Studio on your machine, and if you have installed this this little icon here, which is the live share extension, then it should be able for you to join this session now. And what we have here in our code is an application that actually Sven developed for us. Where is it here? So it's a weather station application. He has also written a little story. If you go check out, the GitHub project later on, we will also have this story in there, so that you can follow on your own to go through this again if you like. This weather station application has a temperature sensor for the moment. And this temperature sensor talks to charts, or in the moment, one chart. We have a console chart, and Sven will show you everything in code right now, so that we can know where we are and what we have here. So at the moment, we only have these two classes, right? We have the application, which controls everything. This is what we see here, our application class, and this is in the core of our application. We have divided up our structure. We have the application core, which is a package here, and then we have a main function or a main module with only these two lines of code here, where we create the application from the core and run it. And within this application and within the core, we have a sensor, the temperature sensor, which has this measure function here, and we can set a chart. And whenever we measure the temperature, it's just a random number that we generate here. Whenever we measure the temperature, then the sensor talks to the chart and tells him to draw itself and to draw the temperature. It provides also the temperature as a parameter here. And within the application, when we started, we have this constructor here, and we create the sensor, we create the chart object, we set some color for the chart, set the chart at the sensor, and then when we run it, we enter a loop, and then every second we just clear the console so that it looks nicely, and then we call the measure function. So our weather station simply consists of the sensor, the application core, which controls everything, and a chart for the moment to show our temperature data. So Sven, is there anything that I missed so far, or should we try to run it?
Yeah, we should probably run it. I think you covered everything we have in our application so far. So let's get to the more interesting part of actually looking at things in the console. You should be able to see the output on your console if you've joined the live share session. However, we noticed that there can sometimes be problems displaying the table chart or other charts when you resize your console. So yeah, don't be surprised if the output doesn't look right at times. A solution for that is what Jan is doing. He has created an editor tab with the console, and that seems to work at all times. So yeah, okay. Anyway, so what we see here in our console is this table chart that shows us a column with the time when we recorded temperature, and in the second column we can see the current temperature. And this is all our application is doing so far. So I guess we can have a look at the next stage in our story.
What I forgot to tell you or forgot to show you is the chart itself. I left this out because we're not so much interested in the details of the charts, but maybe we can also look at this.
We can have a quick look at this.
So there is a lot of code in there, but we don't have to. It's not so interesting for us at the moment. So the most important part is that it has a draw function to draw itself, right? That's the important part. So the rest is not in. So don't bother about the details. Okay, so we don't care about the chart itself for the moment. So what our application looks like right now is like this. Is it large enough, or can you read this? Or see, what is important is the UML diagram. If this is, hope this is large enough. I can make it a little bit more bigger if we like. So, is it okay? Kim, I don't see you nodding. Yes, great, thanks. Okay, so we have this application, and this application is using both the temperature sensor and the console table chart. That's how we call it. It's creating those, and it's building up the structure. It's introducing all the objects to the other so that all this communication can happen. So it's connecting the dots, so to speak. That's what the application itself does at the moment. And it's working fine until now. It's working fine, so no need to improve the structure. Of course, there is things that can be improved always, but for the moment it works. But then comes our management.
Jan, maybe before we continue, maybe we can ask if there are any questions regarding our application before we are starting with the first problem for today. Is it clear to all of you? Could you follow the explanation of Jan and Sven, or should we repeat something? I don't know. By the way, a technical hint. During the live share session, you are able to follow people. So maybe Sven, you can, or no, Jan is sharing. So maybe Jan, you can show it to us.
Yes,
so,
I'm actually. If you click on the live share button icon, which is this one here, if you click on this, then you you get a list of all people which are attending, and Sven is hosting this session. That's why he's on top. And if you click some person, then you follow him, then you see that this dot is actually filled. So I follow Sven. So whenever he switches to one and another file, then also in my editor, I will switch automatically to this file that he's looking at. So we are always looking. So I will always follow Sven. So the main screen here that I'm presenting is always following Sven, so we can see what he's doing. But the idea is that we work together. So that's what we want to do now. We want to get into an interactive session with you. So you should be able, you can try just typing in there somewhere, but just make sure you remove it afterwards or just make a comment out of it. You should all be able to add some code there somewhere. Just do it. Doesn't matter. We can revert, right? So it's in Git.
Probably.
Yeah, also, Kim, feel free to ask any questions. So we are going to work with this example for the rest of the workshop. So
yeah, just unmute yourself and talk to us. It's only a couple of people. Yeah. So, but typing works. So the question now is, we have a feature request. So people are, we have this table chart now, and people are requesting something different, like for example, a bar chart. Is this what we are going to implement, bar chart? Yes, right?
yeah, we are going to
So
implement
that's
bar
what
chart,
we
or rather,
decided upon. We want to have a bar chart. So how do you think, how should we go ahead? How would you go ahead implementing the bar chart?
right, so let's first do the obvious thing, and wrong file. Let's go to the charts file, and there's a magic thing happening. Somebody on our team created the bar chart for us. That's great. So we are already done with that. We have a console bar chart. Yeah,
That was easy.
nice, right? That was easy.
So usually by copy paste, right? Main is copy paste, isn't it?
Yeah. It's a bar chart. It has the same draw method that our console table chart has, of course, with a different implementation. But yeah, so we have two charts now. Our job now is to get this second chart into our application. So any suggestion?
So we don't care too much about the details of the chart. So let's say we have implemented this chart, mostly copy and paste, but now it should, we somehow need to bring it into the sensor. So what's the obvious thing to do? What do you think? What could we do? So now, until now, the sensor has one attribute chart, which takes the console chart. What's the easiest thing to do here? John, what do you think? What can we do?
I would like to add another attribute, console bar chart.
Okay.
It's obvious for me.
Okay,
Just adding the new dependency, I would say.
Go ahead.
Do we want to do that?
Yeah, of course. Sure. I can try.
Yeah. Go on, Sören.
Okay, let's add another chart. Maybe we can call it bar chart. It's from the type console bar chart. Initialize it. And okay, we need another setter. Okay, that's ugly, but let's continue for the moment. Set bar chart, which gets the bar chart, and then we need to set it here. Okay, now we have it. So we have the bar chart and we have the chart, which is the console table chart. And I think now we need to update the chart in the measure method. Yes, here we have the call of the draw function of this chart. And I think I can copy this line also, and we can call draw for all new bar chart. Right.
Okay, does it work?
Well,
Probably not.
let's try to run this. Oh, none-type
Well, that's
object
how
has
I
no-
would do it.
Okay.
None-type object has no attribute draw. Okay,
Okay,
what happened
non-type.
here?
So we don't have the console bar chart imported
Yeah,
yet.
I
Is
think
it
we need
done?
to call
okay, it
set
is.
bar chart in the
Yeah, we
application.
probably need to call set bar chart. Ooh. Let's do this. Set bar chart, and let's create a console bar chart. Console bar chart. I guess we want a color for this. Maybe choose a different color, then let's go with blue. Okay, set the bar chart. Nice. Okay, this is totally gonna work.
That's it? Oh,
Woo!
okay, it works.
Awesome.
Okay. So now what happened so far? I mean, the management wanted to have another chart, right? So and I guess, okay, we made it work, and it works, but we had to make a lot of changes to our core. So all the changes we made have been in the application class. That's what I think, and in the sensor class. Then that's part of the core that we usually don't want to change, right? So we had to change it now, but I'm pretty sure that next week they will come with another chart. So then we would have to change it again. Can we make it somehow independent of the change so that we don't have to change it every time? Do you see an option there?
Any ideas?
I mean, also, I guess this is both charts. They both, I mean, that's what we can clearly see here. They both have a draw method. They both have a set color method. And they are both called chart. I think there is something like an interface cooking in there. Right? Do you agree?
I think so.
Dylan, you're looking skeptical.
No, I'm not sure.
Tim, do you see
Could be.
this interface cooking in there too? So some general structure of charts, some publicly or some API that all charts implement. They both implement draw. They both implement set color or have a color property at least.
Or another question, which principle did we violate here? Is there a principle we have learned which is obviously violated in this example now? If you look at the structure, we have the core application and then we have some other files.
Yeah, I didn't pay any attention, so don't ask me.
Lots of repeated code, of course.
Lots of redundant code, yes, also that. So that's another part, right? So that maybe we can reuse parts of in the chart.
Okay, I think the answer is in the chat. Single responsibility principle. Yes,
Sensor is both
maybe.
measuring and sending to
Maybe.
chart. Yes.
That's not bad.
Yeah. Interface.
So there are a lot of problems, I would say.
Yeah, that's true. Okay, I'd say we go with the first one. The first suggestion.
Let's create a chart.
Let's create a chart. Okay, so since we are considering that we want to talk to all charts in the same way, I think we should probably add this interface to our application core, right?
And where does it belong? To the core or to the
volatile
other
side?
part? The interface. Cohesion with charts, yeah. We had this example with the lamp and the button, where we created a new interface, which we called button server. Interface shouldn't be modified, so
Yeah,
in core.
I agree with Sarah.
Okay, Sven, I think you can create a new file in the core.
Okay, let's
So
call
a
it
new drive.
charts, and let's go with an extra underscore ABC for abstract base classes. And okay, let's have a quick look on how to create an abstract base class in Python. So there's
So
this.
again, we are making this explicit interface way, right? So like what's not common in Python, but it's getting more common. So we make this interfaces explicit using these abstract base classes, right, Sven?
Yeah, exactly.
Oh, okay.
We are doing everything the explicit way. Let's pretend Python is statically typed. So we just call a chart, I guess, if you're all happy with that.
Sound good.
Okay. So in Python, we have to inherit from this ABC class, which stands for abstract base class. And so what do I do in here?
So we are not putting logic in there.
Yeah, I don't think so.
Okay, but is there redundant code? Probably in the
No,
charts.
that's probably redundant code.
So we could make also an abstract base class.
We could do an abstract base class.
So we go with the interface first, right? Because the slides say interface. Okay.
So what do we need in our chart? I have no idea.
I think a draw method, because we always call this draw method.
Okay, let's go with that. So we can mark a method as abstract with this abstract method decorator, and let's call it draw. Doesn't return anything, and since we are not providing an implementation for this method, we are just using the pass keyword. Okay, what now?
So this is like a pure virtual function in C++, right?
Yeah.
Okay.
So what about the set color method? Should it also be in there?
Yeah, it should probably be in here.
Or is it a method or a property? Is it a property, right?
It's a property. We use the property decorator for this. So let's go color. And this is going to return a chart color. And of course, we also have a setup part for this.
Oops.
Okay.
Okay.
And of course, this is abstract.
Color setter.
Right.
Okay, now we have an interface. Maybe we can implement the interface from our existing charts, or to make our existing charts to inherit this interface.
Okay, let's go to the chart.
I think.
And let's inherit from chart.
Yes, Kim, I think that are getter and setter methods in Python. It's like a property which gets the getter and the setter method.
Okay, so now our console bar chart and our console table chart, they are both charts. So what now?
Why do we need a getter for it? Because we can't add a setter without a getter, right?
Yeah, that's true.
Okay, so we
could
need
have-
the
we
setter
could have-
method because we set the color, but we don't need the getter method. So
I
we
think
could
we
also
don't.
stick to
We could
one
just
setter
stick with
method.
a setter method. Yeah.
Okay,
could.
change it.
Want to change
We
it?
don't want to add code that we don't need.
Yeah, but we have this already.
Okay, okay, so that's
So-
probably something we got from others.
Yeah, that's true. Somebody else wants to print the name of the color or something.
Okay, so but in general, you don't want to add code that you don't need.
Yeah, of course. All right. So what now? Are we done? This is
So
a chart
it's-
now.
So now the sensor still depends on the specific chart types. Maybe we can rid of this dependency from the sensor to the subtypes of charts. Maybe we can
Yeah,
now
you
make
think we
it
can
only
just
depend on charts.
replace this chart? Also chart?
So by the way, does it still work? Do all the tests still pass?
Well, let's do our test. Nope.
Okay.
Cannot import name chart color from. Oh, we have a cyclic dependency.
Oops.
So do we agree that the chart color should maybe also be in the core if we can set the color for all kinds of charts?
Yes.
If you say so.
Okay. And let's do this. Let's put it here.
So it
And we don't need this anymore.
probably
Let's import the relevant stuff. And of course, we need to import chart color now in here. And we don't need.
So we don't care too much about this nitty-gritty stuff here,
Yeah,
right?
this
I don't
is-
understand this, but it doesn't matter, right?
Right. It just doesn't matter.
So there's someone
this
in
is-
our team who knows what he's doing there.
Right.
Yeah, okay.
So we have a chart color now in the core. Does it work now? Oh, still works. Great.
Can we go back to the sensor?
Yeah, I think there's
think
still a
we s-
problem here.
We still have a dependency because we
Yeah.
are importing something from console table chart and console bar chart.
Yeah. That's
We have a
probably true.
dependency outside, which is pointing in the wrong direction, I think.
Okay. I think
Maybe we
the,
can remove this.
yeah, the weight is just deleted, right?
Yeah.
Okay.
So now the type hint doesn't work anymore.
Damn it. So what now? Do we just call this chart?
So, I mean, it still says bar chart there. Maybe it doesn't matter if it's a bar chart or a table chart. So we
Okay.
have two attributes, two setter functions. Maybe we can make a list of it.
Yeah, that's probably the better idea, right? Otherwise, somebody will set a bar chart as a table chart, and who knows what that causes in our application. So let's make this a list, I guess. So let's introduce a new attribute. Call it charts, and it's going to be a list of charts. Okay, and I guess we want to add charts to this list.
By the way, we are going too fast and you are getting lost at some details. Please feel free every time to interrupt us and ask your questions or yes. So
Also, you could also write some code. We could also get into more interaction if you like. So maybe next step can be done by someone else.
yes.
So Sven is driving, but someone else can also do the driving.
Yes, but let's get rid of this duplicated code first, and then we can continue, I would say.
Yeah, we
Okay.
would just delete this, I guess.
So here we have a list of charts, and we can add charts and append it to the list, and then
We don't need
we are
this. Just
fine. Yeah, so we
add it
can,
anymore.
our sensor now can work with multiple charts, whatever specific chart is passed.
I
Not
think
yet.
not yet. That's true. I think we still need to change this here in the measure method.
So what's supposed to be there? Someone else now, maybe, if you like. Don't have to, but that's the idea of we need to change those lines.
Grab the low-hanging fruits.
Yeah. Yes. Yes.
So this live share is
Exactly.
pretty nice.
Yeah,
Yeah.
it
Yeah.
works. It's better than GitHub Pilot, no?
Git
GitHub
Copilot.
Copilot. Yes.
Yeah. We have a lot of co-pilots here.
I think we're still missing an underscore here, but I think other than that, everything looks fine.
Okay, so and then try to run it.
Yeah, we can try this. Let's see. Oh, temperature sensor object has no attribute set chart. One of our co-pilots must have broken our application.
I think it's in the application directly, right? So maybe we can go to the application file
Okay.
where we created the sensor. Jan, I think you lost the following.
Oh yeah, you're not following me anymore.
Okay.
Yeah.
Just checked it. Okay.
Yes, that looked good. So no more set chart in our application class. Only calls to the add chart method. So we only accept the abstract base class in our add chart. So our sensor can now deal with both kinds of charts. Let's hope this works. Everything's fine. Okay. So I guess we got this feature request done.
Okay, so what do we have now? Let's look at the slides. I guess this is somehow what we've got, right? We have the application now relying on chart. We have the temperature also now relying on chart. Maybe we can show this to our management. Okay, we got feedback from our management. So I just showed it to them, and they said that there is still some design flaw in there, because we still depend in our application core, we still depend on the concrete classes console table chart and console bar chart. So there's likely to be new chart types in the future. So there's something that we need to do about it, so that we don't have to change the core all the time we add new charts. So to be more specific, they also passed me this UML diagram, which points out our problem. So the problem is that statically, so the static structure that we looked at before here doesn't point out the problem that we have, but we discussed in the beginning, we discussed that when we create objects, we also introduce this dependency. So we still have this direct dependencies on the subtypes of charts because we are creating them in the application. Can you show this in code where we have this problem? If you look at these line here, this is that we create the objects. We are creating the objects, yes. That's the lines of code here where we're creating those objects. So that means that we are still depending on those objects. So the question now is there a way of how we can get rid of this dependency, the process of creating those objects? How can we get rid of this? So one option would be, I think, that we inject those objects when we create the application. We could inject them in the constructor, but as I understood, yes, we could do this, but as I understood the management, they want to have this objects created, or the option to create these bars or these charts, the bar chart and the table chart and what else might come. Yes, it would be a good idea, yes, but it should be, the application should be able to create those objects during runtime. We should be able to switch between the bar charts and the table chart, or decide during runtime which chart to create. So somehow we have to trigger the creation from within the run method, from within the core. So what might be another option to create those objects? New method inside application, yes, but then still, if we do a new method inside application, we still have the dependency within the application. But what's good about this, that we can start with this. Let's start with this method, how to, because then we take, it's the first step. We take out those parts from the application, which is the part that we have to deal with. So we are separating it. We are encapsulating the problem within a method. It's the first step. That's what we could do. Yes, we could create those objects within the method. So we first identify the problem and encapsulate it, and then see what we do with it. So the idea with the method is okay. It's fine. Maybe we call this method create bar chart, for example. So then we encapsulate the problem for the moment. Now add chart, maybe create chart, create bar chart.
Let's go with this. So create table chart first.
Or add is also fine. I don't know. Create table chart, yes. So it returns a table chart.
Console table chart.
Or should it
Could also
return a chart? So
Yeah.
then we would have another dependency to this subtype. We want to have the generic type there, right? So it returns a chart. Too specific. Yes.
Okay,
so now it's more generic when.
So now we just replace it with this. So we are calling the create table chart method to create a console table chart. And
we could do the same for the other.
Yeah, I can do it.
Copy paste is easy.
I would have copy paste is something.
I could have done this too.
Okay. Probably.
Okay, so too specific. Back to square one. I think we come to this. Yes, you are right. We're
getting closer.
We're getting closer. We do this step by step. So let's do one step at a time. So for the moment, we have now identified the problem. We have encapsulated the problem in two methods, but the methods are still within our application core. What can we now do to get those methods out of the core? Somehow we need to get those out of the core into the volatile part, because there is the volatile part is where changes happen frequently. The side related to main. Main is very concrete, and on the main side we create the objects. We are very specific. All these subtypes are created there and then handed into the core. And this part needs to be on the volatile side because it has this relationship to the subtypes. So we somehow need to put it there. So where can we put it? What about creating another object or creating a class where we put those methods? What could a name be for the class? If we create a class where we put this method, Sven, put a class around this and then find a name. And then we put it somewhere else.
I am seeing some very, very good suggestions in chat. Maybe not the last one.
Maybe not the manager. Yeah, chart factory. Yeah, sounds good. Chart factory.
Okay,
let's make a chart factory out of it.
Chart manager.
Okay. Okay, so what now?
So the chart factory.
Chart director.
Chart director. Now we have a chart factory. Now we have to put it somewhere else because it's still in the core.
Okay, let's create a new, or no, let's just take it, maybe put it with the rest of the chart, since it depends on the concrete chart types anyway.
Sounds good.
So let's go away chart factory. Let's put this at the bottom because we need the charts in Python. We need to have the actual types already defined before we can use them. So this needs to go below. Now we have our chart factory, and if we go back to our app, I guess now we just use it. These methods were in our application class before, so we probably need to create an instance of the factory now. Let's try this. So now
we can get rid of the console bar chart, right? On the console table chart import.
That's true.
Here. Okay, so far so good.
So far so good.
Not bad. Okay, let's see if this still runs, right? Okay, everything's still fine.
So is this the final solution, or do you see another problem now? It works, that's good, but what's the problem now? Chart factory is now in the volatile part, and we are creating chart factory in the application, in the core. So now we are directly depending on the chart factory, which is also part of the volatile side. Same as a bar chart, and it's the same module. So how can we get rid of this dependency? How do we get rid of dependencies at all? What do we do usually? In terms of pure Python, we could just simply say, okay, chart factory is the interface itself, and then inject, not create the object there, but inject it probably in the constructor if it would be pure Python dynamically typed. But we want to make it more explicit. We could say factory is the interface, but how can we make the interface more explicit? The chart factory interface, that it is actually adhering, the chart factory is actually adhering to the chart factory interface. How can we make this more explicit using these abstract base classes? Yes. So what we need here, and I hope that you see this, is that we need to somehow do another dependency inversion, introduce another interface for the factory itself in order to decouple us from the changes in the chart factory implementation. So both inheritance and interfaces in Python.
Yes.
Yeah.
So usually, so what we are doing here with the where we define these interfaces explicitly, I haven't seen this in the wild at all, I think. So we just want to make sure that that the interfaces are clearly defined, and as Jan already said, they also serve as a kind of documentation, right? So you always know, okay, this object expects another object that provides these methods that are defined in the interface. Yeah, so in Python, if you have a pure interface that doesn't define, that only has abstract methods, you wouldn't really need it, right? Because Python is dynamically typed and you can just inject any object in there that follows the same interface.
Okay, so we put this chart interface into the charts ABC module, right?
Yeah, let's put it here. Chart factory.
A chart factory interface, sorry, yes.
Abstract
This is where
base
the
class.
chart interface also is.
So, and it had create table chart. That returns a chart. And it also has create bar chart. And that also returns a chart. Okay. Now what do? We go back to our charts, I think, and make this chart factory implement the other interface, right?
Yes. So chart factory should implement
the other chart factory.
Okay, the other
Maybe
chart factory.
let's make this more explicit by
console
chart factory by changing the name.
So that's then to show that it's printing on the console. We could think about, for example, having a graphical user interface chart factory also. Then we can exchange the types. We could have two different versions. One is using the console, the other one is using a real graphical user interface, for example.
Okay, if we go back to our application now, our application class, do we still have a problem?
I think so.
We have an interface now, right? So
yeah,
here, chart factory, easy.
Yeah, now someone might be able to fix it because someone already tried to inject the charts itself in the constructor, but what we now can inject and get rid of the concrete class, the concrete console chart factory, we can inject it. Yeah. Exactly.
Very nice. All right. So now
nearly done. Nearly done. No, not quite.
Yeah.
A little
so,
change.
But we can delete this now, right? Let's do a quick. All right, it's already gone. Yeah, let's just copy this, right?
Yes.
One last step before. Yeah. Let's
yeah,
see.
the imports can yes. Imports can also go. Someone already comment, mark them? Yes. I mean, you can feel free to add code and change it. Just point us to the changes that you made, so then we can all follow on.
I think
And
there's one last thing.
change, right?
And one last change. We expect the chart factory now to be
Maybe
injected.
someone already did the change because the file has been changed. No, not yet.
Need to pass in factory here, right?
Yes. Who wants to do this? Stuart.
Maybe
Yeah.
maybe write this in chat or unmute yourself, because as long as we aren't following you, nobody is seeing this.
Yeah, but go ahead, do it.
Yeah, do it.
It's fine. Yes, Stuart, thanks. Exactly.
Oh, that doesn't quite work. Yeah. From right, and charts
Yes.
is not in our application core, right? That's the volatile part,
Yeah,
so it's not in the core.
So this is the side, the main side, which is the volatile part. There it's absolutely fine to be very concrete. We create all these concrete objects on this side. All the subtypes are mentioned there. This is the dirty side, the factory side, the side that belongs to the mass production companies.
Okay, I think we are done, right? Let's see if this runs. Great. I see charts.
It works.
Nice. Okay.
It works. So where are we now? Let's put up the slide again. Where are we? That's where we are now. That's what we have. So again, we showed this to our management, and they were happy, yes, but still they pointed out one little detail. As there is one aspect that we have not considered yet, and that is we will have additional chart types in the future, as we already said many times, so that they stressed it again. We will have additional chart types, and we would have to change the chart factory interface every time we introduce a new chart type. Can you see why? Yeah, and we always said that interfaces should be stable. We shouldn't change interfaces, because if we change the interface, we have to change every depending class, and this is the core of our application architecture, the backbone, so to speak, of our application. So we should avoid changes to the interfaces. But the problem is, whenever we add a chart type, now we have create table chart, we have create bar chart, then there would be create line chart, create whatever chart. So every time we have to add a new method to this interface and therefore change the interface. Could you imagine? Yes. So yeah. So
exactly.
Exactly. That's the solution. That's what we could do. So Martin was the name, was it right? I only saw Martin there. Kim. Nice, Kim. Great. Thanks. Great work. So Kim already had the solution. So we could make this. If you look at the method name, it already is in there. It's always the same name. Create blah 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 chart, and we make blah 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 just a parameter of the function. So we only have one function name, and pass the type of chart as a parameter. For example, a string. So we just pass the type of the chart as a string, and then it remains just one simple method in our factory that could create any type of chart in the future. Awesome. So yes, let's do this.
Okay. I think now that we've changed our interface and improved it, so it doesn't have to change in the future, I think we need to adjust the implementation, right?
Yes, so we change the interface.
Okay, how do we change it? We have this grade chart method now. How do we know what we return?
Is there a switch statement in Python, or do we have to
Not
go
yet.
with if statements?
Not yet. Coming
Okay.
in a year or so.
Then we have this nesty if statements one after another. So, but a factory is a dirty place, anyway, so it doesn't matter. So we have all these dependencies to these concrete specific classes. This factory has to change. The implementation always is also always subject for change. So it doesn't matter if we have at some place, we have encapsulated this dirty place, this dirty method, this single place where we create everything, where we depend on all these subtype at a single place in this factory. So then we can also have this combination of if statements. Switch is nothing better. It looks slightly better, but it's as worse. Or as bad, or even worse. But because it looks better, but it isn't. Yes.
Nice. We're even getting error messages now.
Yeah. Thanks. Dictionary. Yes, we could make a dictionary, at least for the chart types. The problem now is we have traded a little bit of security because we could pass any string as its type. So we have now, before we had this specific methods for every string, for every chart type. So that would the source for failure is not so large because we have this specific methods. It's unlikely that something goes wrong by spelling the method names because we use type hinting. But now when we use this parameter as a string where we could pass any string, we don't have this type safety anymore. But we have achieved much less coupling. We have decoupled our code quite more. We don't have to do these changes. So this trade-off is good for us because we fail early because someone already added this exception there that when we pass the wrong string, the wrong type, that we fail early. But still, we could make something like a dictionary of types that we could ask for that could bring us closer to another feature request, which is having a menu to select the charts that we should show. So dynamically change the type of charts that we show. So someone is already implementing this dictionary for us, which is great. And then we could start having this menu type of thing that we could then dynamically choose which chart type to show.
The syntax looks great, right? Exactly. Yeah, this is also a great idea to remove the not instantiate the charts in the dictionary because then you couldn't have multiple instances of a console table chart, for example, because we already have the instance in the dictionary. If we just put the type in the dictionary, we can call the we can just call the constructor from the dictionary, because types in Python are just like any other variable. You can pass them around, and if they have a constructor that doesn't take any arguments, you can just put the type in a variable and then call that variable, and it'll be the same as if you would call console table chart directly, for example. So let's do this. We need to change this. So maybe we need to remove that self because we are not currently inside an object. We are inside the class, but we don't have an instance of the class yet. Yes, very nice. That's exactly correct. You can remove this part now. Exactly.
Awesome.
One change that we need, since this is now a static member of the console chart factory. We need to use a type in front of it. Okay. I think that's good. Everybody happy?
What happens now if we pass a bad string to this method? A string we
get
do not know.
We get a key error
Okay.
because it's not inside the dictionary.
Okay, but we get an error.
At least we get an error.
Okay, fine.
Okay, so does this work now? Can I just run this? Oh no. Console chart factory object has no attribute. Create table chart.
Okay, that was, we could
Maybe
have seen this one.
It was to be expected. Okay, what can we change now? We remove the create table chart method, we remove the bar chart, create bar chart method. I guess we can just pass in a string now instead.
There is a nice question in the chat. The best tool would be to have tests, right?
What do you mean?
What do you
mean?
Yeah,
yeah, tests.
So we should, the workshop is only 5.5 hours or something, but we have had to make a decision between using showing you some TDD example or using this design patterns example, but we will have another workshop actually in October, which is also online in Braunschweig, where we'll have this workshop plus some extra and also do the TDD to do it. We will do a TDD example. This is something maybe we would like to attend. I don't know. I think there's already a lot of people having registered there, but we do this a couple of times in this not this year anymore, but maybe next year, of course. So, and we will also talk about test-driven development. Ah, great.
Okay, so back to the topic at hand. Everything works again.
So we are done for today.
Unfortunately not. I remember somewhere in the back of my head, we were supposed to implement a menu so we can, when we call the run method, then that we can.
Yeah, that's actually an important part for us because someone was referring to this. Otherwise, we could have also injected, as we just did with the factory itself. We injected, that's what we call injection. So we injected the factory here to the application inside of the constructor. It's constructor injection. There's setter injection and constructor injection. Injection means you connect the objects with each other. We have now injected the factory because we didn't want it to inject the charts. We could have also injected the charts, but that would mean that we cannot change them when the application is running. We cannot change them during runtime dynamically, decide what kind of bar chart or what kind of chart we want to have, switch from one to the other. The reason why we have the factory is that the factory allows us to create a bunch of objects during runtime dynamically, which means we don't know upfront how much objects we want to have, how much of this kind, how much of that kind. Dynamically create these objects. That's why we injected a factory which does this job for us. Otherwise, if it's statically, if it's always two charts, then it doesn't make sense to have a factory. within the application core to create it, because we could simply inject the charts instead of the factory. Okay, that's the reason why we want to have the reason is why we want to have a menu which allows us to dynamically create the chart objects and decide during runtime which kind of charts do we have to want, or do we want to have, sorry. And that's why we have the factory in the first place, because of the option to dynamically create objects. Otherwise, if it's fixed, we can simply inject the objects, as we did with the factory. We have one factory that we need all the time, so we inject it.
Okay, so as for the menu, so I have a suggestion. This should be really easy, right? So let's do this. Add another method where we could ask chart choice or something, right? So self easy, right? So, and this returns a string maybe, and let's ask the user choose a chart. And yeah, I don't know. Let's print one is, or yeah, let's just ask them. Oh, right here, that's chart type. Right, this is what we are going to do.
Do we have this? You have this dictionary of types. Can we print this?
We could print it.
So then just show which types are there, and then you can choose the index.
But we don't know the console charts factory.
Is it in the? No, someone already made an attribute for it. I saw this.
Yeah, but it's in the console charts factory. It's in the volatile part. We have no idea about this.
It's not in the. Where is the interface? Can we ask
Interface.
for the
Let's
charts?
Maybe we can add a method to ask for the types.
Let's add a method. Okay, let's add a method to the interface to ask for the chart types. What do you
okay.
think?
I think that's okay. So let's create this. And oh, you're not following me again.
Oh, sorry.
I think, or
Okay.
wait, oh no, it was on the wrong screen.
I am.
Sorry.
It's okay.
Yeah, everything's fine. So let's, I don't know, get chart choices. And that's going to return a list of strings. Something like that.
Okay. Yes.
I like this. So let's,
Me too.
Me too.
let's copy this. Right. What now?
Get chart
We have
choices.
this-
Yes.
With this chart types dictionary here, we can access its keys.
That's Python magic.
Python magic. And just to make sure, maybe make sure it's a sorted list.
Python magic as well.
Yes, okay. This is how we get the keys in a nice way. So now we can ask our, oh, let's go to the app. Now we can ask our factory to give us the possible choices of charts. So let's do this. Maybe we can do this, like index chart type in chart factory, get chart choices. And yeah, exactly. We need to create an attribute for that. And so to be able to get the index and the chart type, we can use this enumerate function. So now let's just print it, right? Print index, maybe just Just like this. Chart type. Okay, what now? What do I do with
Run it, run it.
run it?
I'll show it in the run method somewhere.
Oh, show it, you mean okay. So let's put it at the top, self ask chart choice.
Should this return multiple choices?
We could do that. I think in our example, we are going to stick with choose a chart type at the beginning, and we are fine with this.
It's just to show the idea.
Yeah, exactly. Okay, so it quickly printed our chart choices and then exited.
Yeah.
So we probably need to ask
Get some
the
input.
user for some input. Yeah, okay, so chart type. Let's see, does that work? Okay, can do bar. Nothing happens, fine. Should the lines below be removed? This part, yeah, eventually we are going to need this, right? Because we want to select our chart in the run method and not have those fixed charts.
Yes.
So let's probably just return the chart choice from this method. And what can we do with the chart choice now? We can take this here. We can create the chart from our chart choice using our factory. So far, so good. It's just
set some
select,
color. Maybe we
some
can
color.
ask for the color also, so we could do something similar for the color.
You could probably do that.
Yeah.
So maybe create another method, ask color choice, and we are going to get a chart color back. Same here, maybe. Let's go do this, and instead of the factory, we just take the chart color and let's call this color. Oh, let's see. Maybe we want to change this, so we just have to input the number. What do you think about this? That would be easier, maybe. Less code for us. And let's call this. Okay, I think we can remove this now. The chart that we created by hand. And okay, here's a question: should this be self chart factory with an underscore in front of it? Yes, we could do that, but it's not really important. So what an underscore in front of an attribute means in Python is that you would like to be this attribute to be private, but it's only by convention, right?
Yeah.
People outside can still access it. It's just a convention.
But we should do this, right?
Yeah, we can do this.
And also for sensor.
Probably also for sensor. Okay, let's see if this runs. choose the chart type. So let's go with bar, and here I can select the chart color. Let's go with green. Oh, this must be integers or slices, not string. Oh, right. I know what's wrong. Exactly. I think
Stuart fixed it.
no, this doesn't work. String. No, I think this needs to be an integer, right? And then we can remove this here, and maybe now it's working. So let's try this. Oh, key error. Oh, right, I put in the index instead of the. Oh, this is not really working.
You forgot to pass the chart to the sensor.
Right. I think I know what the problem is. I think the list chart color. Oh no, wait. This should.
So we created a sensor.
Oh,
chart.
right. You're right. We forgot to pass the chart to our sensor. See, this happens if you change your application call.
Without tests.
Without tests. So let's go with.
Tests would be great.
Sensor add chart. Whew. Okay, let's hope this works. The bar chart. I'd like a green chart.
Okay.
Yes.
Nice. Awesome. So at this stage, I got a message that actually in this conference there's another talk scheduled for 3:25 or 3:30 or something. So Christopher asked me so that we can finish on time, because they can only host one Zoom session at a time of this kind. So we need to finish on time. But I would have some time left, although we have only covered one pattern yet, which is actually, you might have guessed already that it's the factory pattern that we talked about. Well, we decoupled the creation of concrete types from the core of our application. So as I said in the beginning, creating objects is not as simple as it looks like in the beginning. There would have been more patterns that we could have gone through now in the following. So in the example, we will update. I guess we didn't copy the story to the GitHub repository yet, so we will fix this in the next days so that you can follow on the story. I guess we could also add the slides there so that you have the UML diagrams and go through this again if you like. But we still have some time for some questions. And before we end, we also we are eager to improve ourselves. So we have some feedback Google Forms documents that I'd like. So can you pass the link to the chat, please?
Yes.
It would be great if you could fill out this form so that we can improve our work. So maybe, of course, we are happy if you mention what you didn't like so much, but also we also love to hear what you like best so that we can improve on this too, and we stick to this. And so it would be nice of you if you could fill out this form for us. Hope this works. Did you check if it works? So can you check if it's possible to fill out? Do we need to enable there something? Okay, and before we end, also, so that I don't miss this is also important that you get the reference to the books that we recommend in terms of patterns. Of course, Gov book, Design Patterns. That's the classic book. You should have this on your bookshelf somewhere, but also you can also look for all the patterns on the internet. The information is also there. And if you like the more comic style of explanation, I like the Head First series of O'Reilly. Sören hates it because he don't like the style of explanation. It's a matter of taste, I would say. So it depends. I like it, so I think it's not bad.
Matter of taste.
Yeah. So, and then there is another level again of abstraction. This is the enterprise application architecture patterns from Martin Fowler, also highly recommended. And in case of C++, there is this book which focuses on the implementation of the patterns from the C++ side of view. So of course, every language has its own styles of implementing certain patterns in certain ways. What we did now is the classical way, as it's explained in the Gov book. But sometimes modern languages also adapt patterns and have a certain way of doing or implementing specific patterns. So it's a matter of concept, so to say. So the implementation depends on the language, but it's the common knowledge, the common understanding, the common way of explaining the roles that objects play in the ensemble of all the objects within your application, which is important. So again, we have some time left for questions, if you like. It was fun for me, although I had to talk a lot, and maybe sometimes it was hard for my speech I don't know how to say it in English, so I'm a little bit my how do you say, Stimmbänder? I don't know.
Vocal cords.
Vocal cords are a little bit stressed now, but it was fun for me. I hope you also enjoyed it, and thanks a lot for your attendance. Thanks also to Sören and Sven. It was fun to work with you guys. I like these interactive parts a lot, and I also like that you picked it up and you also helped us building this application. So yes, I enjoyed it a lot. Thank you. And again, we have this workshop occasionally also online. It doesn't matter if you're in Braunschweig or not. So if you go to our website, TU Braunschweig Musen Center, then you can find links to our workshops, and then you can register if you like to learn more about this stuff. Of course, most of it will be the same as today, but we will have this TDD session next time probably, and there would also be an extension of this interactive part. So would be great to see you again somewhere. Okay. So again, thanks a lot. And then I think we can close this down and have this license of Zoom available for the next session. So thank you. Bye-bye. Sören, can you stop the recording?
Yeah.